And if you want, you can turn on the camera.
Yes, it's a very
Huh? Is your airdrop on?
Okay, good.
Oh, you got it? Okay. Okay. Let's copy it here and then we'll start. Okay. Okay. First is next week. Send the papers. Or papers. It's this papers. You can use it like or ask you. Yes. There is Raj. Audio check. No. Krishna is checking on Teams. Yeah, I will do that. Can you hear? Okay. Good morning, everyone. We are ready to get started. Welcome to the 9th edition of the EMC2 workshop. We are the premier venue for hosting discussions around machine learning and architecture. This is our ninth edition, and we are quite happy to be back at ASPLOS because that's where we started our first workshop. Over times, over the last 6-7 years, we have had our workshop hosted alongside both top-tier machine learning conferences as well as computer architecture conferences. We've been at NeurIPS, CVPR, AAAI, as well as ASPLOS, ISCA, and HPCA. And during the COVID years, we had full-day self-hosted events as well, because in-person events were not quite feasible. Now we are very happy to see you all in the room with us. Hope you have good interactive session as we go through the day. Every year, we try to look at what is happening in the community, in the technology, while keeping central to our theme of energy efficiency. Some of the trends and directions that we spotted over the last couple of years are quite evident, but include the prevalence of language models. We are pretty much seeing ubiquity of those chat interfaces across applications. The models are getting bigger as well as being distilled into smaller forms. At the bigger end, we have the GPTs of the world, the Mistrals of the world, whereas on the smaller side, we have some of the Phis and others, Gemmas, as well as the interface through which we interact with them are evolving from just language to include multimodality. We have seen impressive quality in terms of the output of some of these models. But at the same time, we've realized that serving these models at scale is incredibly expensive in terms of cost, in terms of energy, in terms of access to who can actually use them. And that has led to solutions being proposed both in software and hardware. We have seen very innovative techniques and algorithms being proposed on the software front, as well as a whole host of very promising architectures being proposed to tackle the problem of AI computing. And as we go through the day, you will see callbacks to many of these trends and relate to the overall theme of the workshop today. Okay, here's a quick look at the schedule for today. The sessions are divided into roughly 4 segments, 2 mornings, 2 afternoon, with a couple of breaks in between. We will have our posters displayed on the panels. We encourage you to interact with the speakers, the authors, as we go during the breaks. And at the end of the session, in the evening, we'll have a small social event. So please stick around, and we'll hope to connect more casually during the happy hours. A few logistical notes. The sessions will begin promptly. We are a few minutes behind, but hopefully we'll catch up on that. Please be back after every break at the scheduled time so that we can begin and not have to rush through the sessions. For the folks joining us online, please submit your questions via Teams chat. We have our moderators who are looking at the questions, and we will take turns to go between the questions in the room as well as between the audience on the web. For the speakers, since we are having the session streamed over Teams, we will be using a single system for all the presentations. So please do send all your slides to one of us sitting on the front row. That way we will have them ready by the time your turn comes. So please have your slides available with one of our organizers before your session begins. And as we said, posters are available all throughout the day. As and when you find the speakers or the authors nearby, please chat with them, learn more about their work. And first, of course, we wouldn't really have a successful workshop without the active participation of all of you. So please participate through questions, through participating in the panel, just overall interacting with the people, sharing job opportunities, collaboration opportunities, and networking. So with that, we will hand it over to our first speaker. Our first speaker is Amir Gulami. He's He's a research scientist in the Berkeley AI Lab and Sky Lab at UC Berkeley. He received his PhD from UT Austin, working on large-scale machine learning research topic, which received UT Austin's best doctoral dissertation in 2018. He's a Milosh Medal finalist, a recipient of Amazon Machine Learning Research Award, best student paper in SC17, and several others. He's also part of the NVIDIA team for their first time made low precision neural network training possible in FP16, enabling more than an order of magnitude increase in the compute power through tensor cores. With that, welcome, Abhi.
Thank you for joining. Is the slides?
Sure.
All right. Good morning, everyone. Thanks for joining. So today I wanted to talk about Squeeze LLM, which is a work from our lab, dense and sparse transformer quantization. It's a joint work with several other people in our lab. Wanted to shout out to Sehun Kim, who is a last year PhD student in our group, as well as Coleman Hooper, a second year PhD student, as well as the other authors, including Kurt Koitzer, who is my postdoc advisor. So let's first start with this. I don't see the line in Teams, but that's okay. So basically, if you look at what is the main constraint in neural network inference, it's not compute. So back. Sorry, is this in presenter mode or how does this? You go on the screen. Yeah. Just keep on. It has like a animation mode here. Is it not? Okay, there you go. So I'll go from. Okay, sorry about that. So if you look at like how is the basically different compute versus bandwidth has scaled, we see a very interesting trend. So here, x-axis is the year, y-axis is how different things have changed since '98. So if you look at the peak compute available for hardware, and you compare it with R10,000, which is what Jan LeCun was using to train LeNet 5, you see that today's hardware is significantly more powerful in terms of peak compute. So this is how fast we can perform floating point operations if we can have an infinitely fast bandwidth to supply the hardware with data. And you can see a staggering 60,000x increase over the past 20 years with a rate of 3x every 2 years. But in contrast, if you look at how DRAM bandwidth has changed, so starting from GDDR3 in mid 2000 to today, which we have HBM2 or HBM3, you see a significantly slower rate of 100x over 20 years, or 1.6x every 2 years. And same with interconnect bandwidth. So now, every time that the CPU needs to do something, you need to basically be very, very fast in bringing the data. If you're not bringing the data, it's very hard to get good utilization. And because of that, we're increasingly seeing that algorithms are becoming bandwidth bound instead of compute bound. It doesn't mean all of the algorithms are compute bound, but this delta is increasing. So right now the ratio is like, something like, you see like hardware that has like 2 petaflop of peak compute, but it's very, very difficult to get that utilization. So if that's the case, then if you look at the, a lot of the algorithms, it's better to optimize memory instead of compute. So here is one study that we did with BERT and GPT. So if you measure the flops in transformer models for different sequence length, so we're looking at BERT base, BERT large, and GPT, we see that GPT has very small number of flops. So it doesn't require a lot of flops, even at large sequence length. But then if you look at the memory transfer, because we're performing matrix spectral multiplication in autoregressive generation, you see that the memory operations is significantly bigger in GPT. And as a result, when you look at the end-to-end runtime, so when we look at the latency, then the latency of GPT-2 is significantly higher than BERT small or BERT large, because here we're performing a lot of matrix spectral multiplications, which have very low compute to memory ratio, which is called arithmetic intensity. So because of that, if you're able to reduce the memory and don't even touch the compute, you're able to get good latency improvement. So here is Llama 7B. So we're running Llama, sorry. So we are running Llama 7B with sequence length of 128 and batch 31. And if you keep all of the arithmetic in FP16, so you're not touching anything, but then you're reducing the bit precision that you're using to load the weights from 32 bits to 16, then to 8, and then to 4, you see an almost linear reduction in runtime. So the problem is not compute bound. The problem is basically how fast you can bring data to the hardware. And this doesn't, of course, consider the first token generation. So how can we address this memory wall problem? So one of the very promising way to do this is through quantization. But the problem is that if you apply quantization naively, it's very difficult to get good accuracy. So for example, if you do 4-bit quantization, it's difficult to get, reasonable perplexity or reasonable, like, if you're looking at MMLU, for example. And there is an inherent problem with quantization of LLMs, which is around these outliers effect. So if you look at a layer of Llama, this is Llama 7B, and we look at one weight matrix, this is the distribution of the parameters in one of the layers. So you see a lot of outlier values, and these outlier values create problems when we're doing quantization. So when we're doing quantization, we have a range. So here, let's say a hypothetical range of -5 to 5. And what we're doing is we're mapping this, for example, in 8-bit quantization to -127 to 127. If this range is very large, then the resolution that I can put the bins or this 8-bit quantization is going to be very coarse. And when we have outliers in LLMs, this is going to increase this range significantly. And so many people have looked at this, like there was an LLM.int8 paper that looked at this. There was a couple of other papers where they were trying to do rescaling to adjust this. But there is an easy way to address this using ideas from robust compression, so robust PCA. So what we can do is basically we can take the weight matrix and do this kind of decomposition of what we call dense and sparse. So if you look at this weight distribution, there's only a very few number of parameters that are very large. It's not a lot of parameters that are very large. So what if we can take this out? So we basically take all of these outliers and we represent them as a sparse format. We know how to do sparsity very efficiently. So here we're not doing pruning, but we're basically taking out parameters and preserving them. So if you take 1% of the sparse values out, then what we get at the end is a very well-behaved set of parameters in a very small dynamic range, which allows us to do very low precision quantization. So basically, the first idea is to perform dense and sparse quantization. And so for people who are familiar with robust PCA does low-rank decomposition, but here we're performing sparse decomposition, which may not be low-rank. So what we can do is basically 99% of the values will be basically very well behaved in a very small range that can be quantized. We represent that with matrix D, and the rest of the parameters is going to be represented with this matrix S, which we can store very efficiently using CSR format or your favorite sparse representation. And then when you're performing the multiplication, the good thing about this is when you're doing this dense and sparse multiplication with X, you can perform this multiplication in parallel. So while you're performing the dense multiplication, you can also perform the sparse multiplication in parallel. And so how that looks like is basically given a set of weight values, we perform non-uniform quantization to get the quantized representation of the dense component. We have the outliers. During inference, we basically perform a dense matrix multiply for this part. And for the sparse component, we can call q-sparse, so you can write even specialized kernels to do this. But you can perform this in parallel, so there is very little overhead for doing this. The second thing is, for a lot of applications, we were using uniform quantization. So, if you have a paper like in 2021, we said why would you even not do uniform quantization? Because you can get benefits of doing multiplication in integer arithmetic, and that's great. But it turns out that because of these outliers and sensitivity of LLMs, you do need to perform the computations in higher precision. But that doesn't really matter because compute is really fast. So whether you're performing them in FP16 or you're performing them in int8, that's not the bottleneck. So basically, we want to perform it in FP16 to avoid performance degradation. And if you're doing that, then there is no reason to perform integer quantization. So if I give you this weight distribution, like a Gaussian distribution, uniform quantization splits this range into uniform number of bins, right? Uniformly spaced bins. Which is great for doing arithmetic in low precision. But because we are not doing arithmetic in low precision, we can perform non-uniform quantization, which is basically, I can put these beans where I have more values. So, this is a Gaussian, there's more values represented near zero, so we put more beans around that. And so non-uniform quantization ideas were floating around, like, there was a lot of papers in 2016, 2017, but they never picked up because always for CNNs, we wanted to perform arithmetic and integer arithmetic because, we wanted to get the compute. But here we're moving to non-uniform because the problem for a lot of cases is memory bound. But how do you compute these beans? So, for Gaussian distribution, I'm sure all of you agree that, we want to put more beans near where more parameters are, right? Do you agree on that? So obviously, we don't want to put a lot of beans, like near where there's very few parameters. So what usually people did was basically you have this weight values W. You want to find this quantized representation of these weights such that this is minimized. Basically, the L2 norm, the L2 difference between the original weights and their quantized representation is minimized. But it turns out that not all weights are the same. So it turns out that some of the weights are more sensitive than others. So here is a representation of how the loss function look like if you're perturbing the parameters across two random directions. So you take one parameter, you perturb it across two different directions, and then you see how is the loss changing. So the z-axis is essentially lost. You see that when you're perturbing this parameter here, the loss is changing very rapidly. So even a very small change in this parameter is going to result in very large perturbation in the output of the network. But if the parameter is not sensitive, then even large perturbation there doesn't matter. So if you have a lot of parameters which are insensitive to perturbation, then there's no reason to put a lot of beans close to them. So that's the idea of sensitivity aware quantization. So instead of just looking at this loss, instead of just looking at this loss of W minus WQ, what if we find a weight and we weight the sensitive values more, so we're making less errors when we're quantizing them? It turns out that we can easily do that with Fisher information. So the idea is what we want is to minimally perturb the output of the network. So we want the loss of the function of loss of the neural network after quantization, LWQ, to be very close to the loss before quantization. So the output of the network, we don't want it to change, but we can perform a Taylor series expansion around quantization WQ. We get the first order term and the second order term. Gradient is zero, so this term will be zero. And so we will be left with this term. Basically, the perturbation of the loss will be equal to where we are, plus the magnitude of the perturbation. Obviously, larger magnitude will result in more perturbation, but importantly, it's going to be weighted by the second order derivative. If you have a very sharp loss function, then that's going to multiply this very large to a very large value. If the loss function is very flat, even if you have a very large perturbation in W, still the loss is not going to change. So we can use this as basically a metric to avoid quantizing sensitive values. So basically now, instead of just looking at W minus WQ transpose W minus WQ, we multiply it with the second order derivative, Hessian, and we can also approximate the Hessian very well with Fisher information, which is essentially gradient squared. So this is essentially what we're going to end up minimizing. So if you have a very sharp loss function, the value of f will be very large. So you will penalize that more. So you end up putting the signpost much more closer to those points. And if you have values of fi which are small, loss landscape is very flat, then you end up, allowing a little bit of perturbation there. Okay, so putting these things together, if you just go from integer quantization to non-uniform quantization, this is llama 7b with 3-bit quantization, you see that the perplexity on C4 dataset goes from 28 to 18. Then if you add this sensitivity-based quantization, we get almost 10 perplexity point improvement, which is amazing. So just going from quantizing W minus WQ, which is what people are doing, by weighting the sensitive values, we're able to significantly get better perplexity. Then if you perform this dense and sparse quantization, so now from sensitivity, we also go and remove the outliers with this dense and sparse decomposition. So this is the original weight distribution. We remove the outliers as a sparse format, compute the arithmetic in FP16, get everything else in dense component, quantize them, load them in quantized format, perform arithmetic in FP16. We're still able to get further reduction of perplexity. So how does this compare with other methods? So the other methods, most of them use, variants of GPTQ. So they group the parameters so that they're in closer range. They do some reordering so that when you're quantizing parameters, like the outliers are close to each other, so the dynamic range is small. They're interesting methods, but it requires a little bit of special treatment. Like there's you have to be very careful with GPTQ's ordering. If the ordering is not right, the accuracy will be low. If you try to do reordering, that has some overhead. But there's also AWQ, which uses activation to detect where the outliers are, activation-weighted quantization. But what we found is that across the board, a squeeze LLM is able to get better accuracy. And the reason for it is the non-uniform quantization with sensitivity, aware quantization, as well as this dense and sparse decomposition. So what we're seeing here is variance of llama quantized to 3-bit quantization. Y-axis shows perplexity on C4. GPTQ, so lower is better. GPTQ is here, so you can see the green curve. This is AWQ, closer to GPTQ, a little bit better, and this is squeeze LLM. But I want to say that one benefit of AWQ is that it doesn't require this dense and sparse decomposition. So it's almost a placeholder for GPTQ. So that's an advantage of their method. But if you want better accuracy, you can perform this dense and sparse decomposition as well as that sensitivity aware to get the extra accuracy benefit. So putting everything together, we were meeting with a couple of these hyperscaler companies before, for people who are in quantization, probably this may sound familiar, and everyone was saying that we don't want any accuracy drop, right? So if you have this object detection, if you do quantization, even like a little bit of accuracy drop, we can't accept that. And we kept telling them the accuracy is not dropping. Actually, you can quantize a bigger model and get better accuracy with whatever latency you want. But that never registered, right? Everybody was like, okay, what's the baseline accuracy? But with the LLMs, it's very easy to show that after quantization, your accuracy increases. So here is a perplexity result. The x-axis is model size. So y-axis is perplexity. The red curve is the baseline models without quantization. Again, lower is better. So if I take the 13B model, and let's say you're a practitioner at Google and you want to quantize this, and you only have, let's say, 20 gigabyte of available memory. You can either go with the 13 billion parameter model, or you can go with the 65 billion parameter model and quantize it to 3 bits. You end up getting better results if you start with the 65 billion parameter model. And so this plot, is like, when we got this plot, I was very happy because now this clearly shows that quantization allows you more freedom in choosing better models rather than, everybody was focused on just what's the baseline accuracy with 65. Oh, it's like, let's say 565. Now you have 0.1 perplexity draw. We can actually tolerate that. Now a lot of people are actually seeing this picture, and I'm very happy about that because every time we're getting this question of what's the delta with the baseline, and especially when we're going to low precision, people were asking if that's going to be useful. Just one more topic. So we've extended this also to KV cache quantization. It turns out that also the KV cache has a lot of outliers. So when we started this work, a lot of people were focused on short sequence length inference. This was well before newer models that came with long context. And we were looking at different problems. Like, a lot of people were using RAG to effectively perform long context inference, right? They were performing those things. So we asked the question that, is this really going to be like this, a year later? Maybe we can enable long sequence generation. And we looked at the overhead, and it turned out that the overhead is in KV cache values. So these are the different models, throughout the years, starting from the BERT model here, which had 512 sequence length. Llama model had around, I think the original one had 2K or 4K, and newer models. The question is, if you can get more sequence length, if you can get more context, it can enable a lot of interesting applications. You can have, the whole code base, for example, for GitHub Copilot, you can have much bigger part of the code base analyzed by your model. or you can basically effectively remove RAG, the need to do RAG for a lot of applications. But it turns out that one of the overheads of enabling long context is KV cache values. So if you look at the memory consumption for long sequence length, if you have very small sequence length of 512, the majority of the weight is what, the weights are going to be the majority of the memory consumption. So 98% of your memory consumption will be the weights, and only 2% will be in KV cache values. But when you go to a sequence length of 128K, that completely changes. Now, if you look at the footprint, 84% is going to be in keys and values that you've stored, that you have to fetch every time, and only 16% are going to be the weights. So this KV cache is becoming a major bottleneck. And there's a lot of interesting work on, state space models like, Mamba. There's this work called Jamba that's coming, that's reducing this overhead. But we asked the question of, what if we just quantize this to very low values? Can we do the quantization? And it turns out that actually the KV values also show this outlier effect. So this is also related to the massive activation paper that showed that for some tokens, you see very large activations, and initial tokens, we also see very large activations. So we asked the question of, what if we perform this density sparse decomposition here and perform very aggressive quantization for the keys and values? So what you're seeing here is Llama 65B. You see the values, the distribution of the values across the channel and token. If you perform this density sparse decomposition, remove these sparse outlier values, so only 1%, you keep them in FP16, the rest of the values are very well represented. So you can quantize this to very low precision without any accuracy drop. And we showed that you can actually go down to 2-bit precision. But the key challenge here is, how can you perform this? The activations are coming dynamically, right? Weights are static. You can do any kind of algorithm you want. But here, the activations are real time. Like, they're coming, the distribution could be different. So we spend a lot of time on optimizing the algorithm so you can perform this in real time. And interestingly, the derivation of the sensitivity remains the same, but with a little bit of a tweak. So when you're performing this calculation of, we wanted to minimally perturb the loss after quantization. We didn't want the loss to change a lot. Turns out that, obviously the gradient with respect to weights is 0 at convergence, but the gradient of loss with respect to activations is non-zero. But here what we want, because we're not dealing with one activation, we're dealing with a lot of activations, we want the expectation of this change in the loss after quantization to be minimized for all kinds of the deltas that we see in activation quantization. So different sentences come in, we quantize them, and we want on average, we want this to be to not be perturbed when we're quantizing the KV cache values. And it turns out that if you expand this and you assume that the distribution of this delta of quantization is a Gaussian with 0 mean, you can get this Fisher sensitivity metric similar to the squeezed LLM. So basically what you end up doing is you try to quantize values that are not sensitive. So many of the keys and values are not sensitive. Like in a sentence, a lot of the values, like, a lot of, the and may not be very important. So you don't really need to store them with very high precision. But a lot of other values are very important, like, like new lines are important, let's say, dot full stops are important. But you basically weight them with higher sensitivity, which you can automatically calculate with Fisher information. So with this, you can actually go to very low bit precision quantization. So I think I'm almost out of time. I want to thank the organizer for inviting me. Thank you for listening.
So very nice talk and very nice. A question I have about the dynamic quantization in KV cache. You show us the high level algorithm, but how do you execute the efficiently?
Yeah, that's a great question. So we looked at, specifically, we looked at keys and values, and it turns out that each one of them has different patterns of where the outliers look like. For some of them, certain number of channels always show certain outliers, so you can pre-compute those. We found that if you perform, for keys, for example, we perform per channel. For values, we do per token. We found that if you have a small calibration data, you can perform this, you can compute this dynamic range very efficiently offline, and then you have that. For the Fisher information, it's pretty easy to calculate that because you just get the gradient with respect to the activations. Then the question there becomes, how fast can you perform the k-means to compute where to put these signposts? We found that for like normal applications, like, that you're running on language data, like Wikitext type data or C4 data, you can compute those lookup tables and store them statically. So you don't need to compute those k-mean values real time. But for some other applications, like code or some other things, you may want to perform this offline on a CPU, for example. You don't need to immediately calculate that while you're doing the autoregressive generation. So you have two options. Either you offload that, for example, to the CPU to perform the k-means, and CPUs are very good at that because k-means itself is memory bound, or you can compute those lookup tables offline and use those when you're doing the inference. Great question.
Used to separate them or decompose them? Is it some kind of physical ways?
Yeah, great question. So for the first one, we are not quantizing the activations because we were more focused on, like, after first token is generated, what's the bottleneck basically. So if you're looking at that, then you're memory bound, you're not compute bound. That's not necessarily true when you have very long prompt because the first token will be compute bound. So quantizing activations can help you there. But we found that there's some accuracy degradation if you start looking at activation quantization. So all of the activations are kept at FP16, but they're loaded in lower precision. So your basic load time will be better. What was your second question? How do we perform this decomposition of sparse and dense? Great question. So for that, we do two things. The first thing that we do is basically look at the magnitude of large values. Obviously, a value that's very, like, 2 orders of magnitude larger than everything else needs to be removed. So you can do that with percentile, calculation. The second thing that actually is important, if you look at this plot, and I didn't explain this in the talk, like a lot of the value, there's the small values here that you also can remove. So these are very highly sensitive values. So it turns out that some of the values, even if they're very small, they're extremely sensitive. So you can preserve them still in that sparse format, but putting it in as part of the sparse matrix. So the sparse matrix contains two things: outliers, as well as values where the loss landscape is very sharp, which we can compute from the feature information matrix. Great question.
Let's thank our speaker.
Thank you so much.
You mentioned briefly MAPA, and we have just the right person to talk about it. Our next speaker is Sri Dao, the incoming assistant professor at Princeton University. He's currently chief together with us. He did his PhD in computer science at Stanford. He works at the intersection of machine learning and systems, and his research interests include sequence models with long range memory and structured matrices for compact deep learning models. Over to you.
Thank you for the kind introduction. Hi, everyone. I'm really excited to be here. So this talk's going to be the intersection of machine learning and systems. And there's been a bunch of really exciting results, especially recently. So I'm just here to share some of these results. And the theme is hardware-aware algorithms for sequence modeling. So we're going to think about algorithms that take advantage of the hardware that they run on for efficiency. So just to motivate some of this, we've seen that machine learning has made a lot of exciting progress. You've probably heard about a lot of this already. There's been a bunch of tasks that we thought maybe 2 years ago were really difficult, and now we have actual systems that everyone can use to solve some of these tasks. So an example is fixing bugs. You can go on ChatGPT, Claude, maybe Llama 3, and you paste in a snippet of code, and it would tell you where the bugs are and how to fix these bugs. In image generation, you type in prompt. The model takes a fraction of a second. It will generate a painting for you. In other domains, like drug design, for example, the folks at DeepMind have done such an amazing job with AlphaFold and AlphaFold 2 that lots of companies are now using these models to predict protein structures to accelerate drug designs. So these are great, and we want to understand what enabled these advances, what are some of the outstanding problems, and how do we address some of these outstanding problems. So the narrative in the past 5 or 6 years has been that scale that brought about quality and capabilities. So in terms of model size and the amount of data that they train on, in the past 5 years or so, we've seen models getting 1,000 times bigger from BERT back in 2018 at 300 million parameters. And now we have, for example, GPT-4 is reportedly at the trillion parameter scale. And as these models are get bigger and train on more data, they do better and better on existing benchmarks. So they get higher quality. But what's amazing is that they seem to have new capabilities. So here's an example of language models able to explain jokes. So I put in this joke. I tried 10,000 random restarts of my neural network, but I was accused of overfitting. I guess no good seed goes unpunished. And I tried this with a 1B model, and it didn't understand the joke. And when you try to ask it to explain the joke, it would just repeat the punchline. But if you try it with a much larger model, a 175B model, then it does understand the joke. It does understand this is a pun on no good deed goes unpunished. And so this is amazing. Scale is now more closely tied to advances in machine learning than ever before. And so with efficiency, with scale comes one core challenge, which is efficiency. And given that you're at this workshop, I don't have to do much to convince you to care about efficiency, but I just want to share my perspective on why we work on efficiency. And the first reason, kind of obvious, is efficiency makes it easier to train and deploy models, and more importantly, to conduct research on these models. So we have a bunch of large and slow models that do really well. Can we get to the point where we have a bunch of smaller and faster models that do just as well? The second reason, more importantly, I think, is that efficiency can unlock new capabilities. So an example is was GPT-3 Playground maybe a year and a half ago, where if you asked it to write a 4,000-word essay on the best ice cream flavor, it was not able to do so. Not because the model was not smart, simply because it couldn't process anything longer than 4,000 tokens. And so as we see, I would try to convince you that this is actually an efficiency problem. And if we can solve this efficiency problem, we can unlock, for example, long context. And we've seen that playing out in the last year or so with model context getting longer and longer. So my approach, or one idea to tackle the efficiency problem, is to design algorithms that take advantage of the hardware that they run on. So I'll show two examples. One is I/O awareness, which means you want to design algorithms to reduce reads and writes to GPU memory. And as Amir mentioned, memory is a lot of times the bottleneck. And for illustration, I'll talk about flash attention, which is a fast and memory efficient attention algorithm with no approximation. In the second half, I'll talk about a similar idea applying to a different class of model. So the idea is state space expansion, where we expand the recurrent states in SRAM to avoid memory cost. And that leads to Mamba. This is a selective state space model that can match transformers on language model, but with fast inference and potentially long context. So this was joint work with Albert Gu. So we've been very lucky to have a lot of folks adopting our research. So flash attention is now available in PyTorch. The folks at OpenAI really liked it, so they implemented it in their language. Triton, folks at Meta, NVIDIA, and Microsoft, and a bunch of companies have been using flash attention for LLM training and inference. So the talk will have two parts. The first part is on flash attention, the second part on Mamba. And so for the first part, I'll talk about attention being bottlenecked by memory reads and writes. And as Amir mentioned, this is now kind of the understanding with the current hardware where the bottlenecks are. And then I'll talk about some of the strategies to address this bottleneck. And then I'll show some results. So the motivation, what is the problem we're trying to solve with scaling model? One direction is we want to model long sequences. And so why do we care about this? So there are three main reasons. One is it can enable new capabilities. So in NLP, you might need large context to deal with books and plays and code bases. The second is to close the reality gap. So for example, in computer vision, you might want to model high resolution images, which can lead to better and more robust insights. But high resolution images will lead to really long sequences. It could open up new areas. So in a bunch of areas like time series, audio, video, medical imaging, data is naturally modeled as sequences of up to millions of steps. And the dominant architecture right now, Transformer, has a hard time dealing with such long sequences. So if we can design algorithms such that these Transformer models can deal with long sequences, we can open up these new areas. Okay, so what is the problem? Why can't we just increase the sequence length or the context length? And I would argue this is an efficiency problem. So in terms of terminology, context length, we're doing sequence-to-sequence modeling. So context length just mean for each element in the sequence, how many other elements does it interact with? And so here's an example where if you just brute force and increase the context length, it could slow down or completely stop training. So I take an example of Megatron LM, which is a code base from NVIDIA that's been used to train large models. So, and I'm measuring training efficiency on A100. That's the y-axis. You can think of it as proportional to how many tokens per second you're processing. So in this case, if I train a 1B model or a 3B model, I get pretty reasonable training speed on A100 with 2K context length. But if I increase the context length to 8K, what happens is the 1B model slowed down significantly, around 2x slower, and the 3B model run out of memory. So we couldn't train the 3B model with 8K context at all. So that means that the issue here is we want to figure out how to efficiently scale models to longer sequences. It is an efficiency problem, and I'll show some of the ways we can address this. So just a little bit of terminology. I'm sure most of you are familiar, but just so that we're on the same page in terms of terminology, we're going to focus on the attention layer in Transformer. So Transformer usually will have a bunch of blocks, encoder blocks or decoder blocks, and each block has two main layers: the attention layer and the MLP layer. And I'll focus on the attention layer because that's if you want to scale to long sequences, the attention layer gives you more headache. The MLP layer is relatively straightforward. So what does the attention layer look like? So we're given the query and the key, and these have shape n by d, where n is the sequence length on the order of thousands, and d is the head dimension, usually 64 or 128. I'm talking, if you're familiar with multi-head attention, I'm talking about one head of the attention mechanism. So what you do is you multiply the query and key to get the similarity score, and this has shape n by n. So this is a pairwise similarity. So for every pair of query and key, you compute how similar they are. And then you normalize the similarity by applying softmax, so to get the attention probability. And the softmax looks like for each row, you exponentiate, and then you divide by the sum of the row so that everything is positive and sum to 1. And then you multiply with the value matrix, which is also given, and this has shape n by d as well. And you get the output of shape n by d. So we see that the inputs and outputs are all n by d, so relatively small. But we have these intermediate matrices of size n by n. And because of that, attention is going to scale quadratically in sequence length n. So this is the core difficulty, is that if you increase the sequence length, double the sequence length, then the amount of compute and the amount of memory you need would increase by 4x. So that's why it's been really challenging to scale to longer sequences. And ever since Transformer became popular in 2017, there's been lots and lots of great work approximating attention. And I worked on in this area as well. So there are a bunch of great work from folks from Google, OpenAI, and other places on approximating attention matrix. So there are two main lines of work. One is using sparsity. where you assume some of the entries of the attention matrix is 0, so you don't compute some of them, and then you only compute a few of them. So here I'm using the purple purple cells to denote. You decide beforehand that you're going to only compute the attention values for these purple cells, and if there are few of them, then you save on compute and memory. So the other direction is you can assume some kind of structure for the attention matrix, and maybe after some nonlinear mapping of the query and key, it's approximately low rank so that you can associate on the right. So you would do k times v first and then multiply by q. And of course, you can combine these things as Amir mentioned, usually sparse plus this kind of dense or low rank can work well as well. And the goal here is to approximate attention to trade off quality for speed. But after working on this for a while, I talked to some of the practitioners who train large models, and they say we usually don't use these methods for large scale training for two reasons. One, they lower quality, and two, they are not necessarily faster. So they would reduce the amount of flops, but they're not necessarily faster. So this was surprising to me coming from a machine learning background. So I thought, as long as we reduce flops, it should run faster, but that turned out to be not to be the case. And so we wanted to figure out if there is a fast and memory efficient as well as exact attention algorithm. So that's our goal. And so to get there, we need to understand what the bottlenecks are. And as I mentioned, the bottlenecks are that we have these intermediate matrices that are of size n by n. And turns out most of the cost is actually just reading and writing these matrices. It's not computing them, it's reading and writing. The biggest cost is in moving the bits. A standard implementation would materialize these matrices in memory. And so you would need to, for example, you need to write this intermediate similarity score to memory, and then you need to load it back up to compute the softmax, and then you need to load A back up to multiply by V. So that turns out to be the most important bottleneck, which is memory. And so how do we deal with this bottleneck? We just need to understand a little bit of how the hardware works. So here's a crash course on how GPUs work. And if you're interested, I highly recommend this blog post from Horace He, Making Deep Learning Go Brr from First Principles. This is kind of best bang for buck. You spend 10 minutes reading this, and you understand kind of the hardware aspect of deep learning much better. And Horace also giving a tutorial on PyTorch Inductor. I think in this today in one of the PyTorch tutorial workshop. So I recommend that as well. So okay, how do GPUs work? So here I'm drawing the green box as HBM, or what you think of as GPU memory, high bandwidth memory. Usually, if you type NVIDIA SMI, this will give you, I don't know, 40 gigabytes, 80 gigabytes, something like that. So that's the HBM. But GPUs also have these compute units. I'm drawing here in purple, and SRAM sitting close to compute unit. Here I'm drawing in orange. And there's a big difference between SRAM and HBM. Usually HBM is orders of magnitude larger than SRAM, but SRAM is usually an order of magnitude faster. So this is the usual memory asymmetry, memory hierarchy that also show up in CPU. There's DRAM, there's L2, L1 cache, and registers, and so on. So this kind of memory hierarchy is ubiquitous. And so how do things work? The inputs start out in HBM. It then get transferred to the compute unit or SRAM to do any kind of computation, and then it get transferred back to HBM to write out the output. So this is exactly why the memory bottleneck is so painful. You got to just keep moving data back and forth between the HBM and the compute and SRAM. Okay, so how do we deal with this? We can exploit this asymmetry to get speed up, and we want to design an attention algorithm that is I/O aware. That is, it takes into account of the reads and writes to different levels of memory. So the classical technique to do that is computing by blocks, also known as tiling, blocking and tiling. This is what people figure out when they started implementing matrix multiplication back in 1970s and 1980s. But what are the challenges? So lots of folks have been trying to do kernel fusion on attention for 5 years or so after attention transformer came out, but they face this difficulty, which is there is this softmax normalization that's really, really annoying because it kind of couples the entire row, so you can't just break it up into smaller pieces. And if you want to train models in the backward pass, you need to compute gradient, and to compute gradient, you need these intermediate activations like the score matrix or the attention matrix. And so how do we deal with this? So we restructure the algorithm to load block by block from HBM to SRAM to compute attention. And we use this trick called online softmax that actually people have figured out 4 years ago. That allows you to rewrite the softmax mathematically in an equivalent way that computes softmax of a local block and then rescale it to get the global softmax. So that's how we deal with tiling, basically combining the classical idea of tiling with online softmax, which is a mathematical rewriting of softmax that people have also figured out. In the to deal with the second problem, we do recomputation. Yeah, this is conceptually quite simple. We don't store things from the forward pass. We recompute them in the backward pass, and that turns out to work quite well. So I will skip some of the way this works precisely, but the way we proceed is that we compute things by block, and as long as you load one block from HBM to SRAM and compute, and then you do a bunch of computations there before writing down the output, you avoid this intermediate reading and writing of to memory, and that's our goal. So that's the forward pass. In the backward pass, here I'm showing what we store and what we don't store. So we store the Q, K, and V as well as this softmax normalization constant. And we don't store these intermediate matrices. So in the backward path, what we do is once we load in Q, K, and V, we recompute these on chip. So and the intuition is that computation is cheap and a memory reading and writing is expensive. And as long as you have this softmax normalization constant, which is quite small from the forward pass, you can recompute all of this pretty quickly. So here's an example of comparing standard implementation and flash attention. And in terms of flops, flash attention actually incurs more flops. And it's because we do recomputation in the backward pass. But in terms of memory reads and writes, in this particular case, is 9x fewer reads and writes. And as a result, it runs 6 times faster. So this is somewhat of a counterintuitive result that you can speed up the backward pass if you increase the amount of flops. And as Amir mentioned, this kind of thing shows up in other places as well. So how well does this work? So we get about 2 to 4x speed up compared to an optimized baseline in a bunch of different scenarios, in a bunch of different sequence lengths, whether you have dropout, masking or not. And there's no approximation, so lots of folks have been using this to train large models, and it works just fine. In terms of memory is now linear instead of quadratic in sequence length, simply because we don't store the intermediate n by n matrices. And so that was flash attention 1. We came back and kind of optimized that a little bit more, thinking about the hardware side, how to better parallelize the computation, how to partition the work. So the key idea here is we rework the algorithm a little bit to reduce the amount of non-matrix multiply flops, because GPUs and other accelerators have specialized units that do matrix multiply very, very quickly. So anything that's not matrix multiply turn out to be relatively slow. So all the softmax rescaling, the exponentiation, and so on can contribute quite a bit to the runtime. So we rework the algorithm a little bit to reduce some of this non-matrix multiply flops, and we parallelize them better to improve occupancy on GPUs. And we also have better work partitioning between warps to reduce communication. So this is leaning more on the understanding how GPUs work or how accelerators work to speed things up. And as a result, we're able to get about 2x speed up on A100. So we can reach maybe 200 teraflops per second on A100. that means that we can train models with 2x longer context length for the same cost. And if we're already at 200 teraflops per second on A100, A100, the maximum theoretical flops is like 312 teraflops. So we're pretty close to kind of device theoretical limit. Since then, some folks have taken this and optimized this further for H100 GPUs. So Ganesh and Jay, they have very deep understanding of these low-level GPUs features. So using things like the WGMMA instruction, using TMA to load from memory much faster, and using FP8 to use to have lower precision and higher throughput. And they're able to on the H100, they're able to reach almost a teraflops teraflops per second with FP8. So this is awesome. I didn't expect that we can push the efficiency that high on the H100. So that was optimizing for training. For inference, inference is also an important workload. And so far, the bottleneck for training is that you have these big matrices n by n. But for inference, especially for decoding, you're decoding one token at a time, a couple tokens at a time. So you can think of query is very short, and the key and the value are very long. So as Amir mentioned, the KV cache will occupy a lot of memory. And for example, at Together AI, we're doing LLM inference, and 80% of our problems are dealing with KV cache. So previous methods, what they do is that they have this sequential dependency where they would need to load the KV cache from left to right. And if the query is very short, there's not enough parallelism to load in the KV cache quickly. So we changed this a little bit. This is in collaboration with some brilliant folks at Meta. So what we do is we use the same softmax decomposition trick. We split it, in this particular case, we split it into 5 parts and load those 5 parts in parallel by different thread blocks of different workers to improve occupancy. And then we have a separate step that will do the reduction to combine the results. So the goal here is to load the KV cache as fast as possible. And as a result, we're able to get 2 to 8x faster end-to-end generation on CodeLlama, where the context length is very long, 32K to 100K. So this is important for workloads where you're things like Copilot that needs to do inference over a very large code base. So I will skip some of these results. And the upshot is that we can have a fast and memory efficient algorithm for exact attention. The 2 key ideas are tiling and recomputation. And the upshot is we get faster training, better models with longer sequences. But so far, we spent a bunch of effort optimizing for transformer. But at the end of the day, if you scale so super duper long sequences, you still have to pay this quadratic cost in terms of compute. So we've saved memory cost, but we haven't really saved the compute cost. So for the next part, I'll show some of these. So how some of these ideas also apply to state space models, which scale linearly in sequence length. So these are very much inspired by RNNs, recurrent neural networks, where they have this natural autoregressive way of for each time step, you kind of summarize the information into a hidden state and then pass that hidden state to the next time step. So this is more natural for autoregressive modeling, but this was slow on accelerators and was hard to optimize. So this was one of the main reasons that kind of transformers took over in 2017. Transformers with attention, they have this dense interaction. Any pair of query and key can interact with each other. But that does mean that it's quadratic time in training and linear time per inference step. So with selective state space, which is this core layer of Mamba, we want the best of both worlds. So we want efficiency, but we also want it to perform really well. And if we can do both of those, we can scale up to long context. So here's a brief idea of how this works. So the modeling on the modeling side is actually quite simple. So the model is described, the core model state space is described by this equation where you have this hidden state H that is that depends on the previous hidden state as well as the input X. So you take X, you multiply by this matrix B, and then adding in the information from the previous hidden state. And then given the hidden state is usually much larger than the input X. Given the large hidden state, you then project down using this matrix C, and then adding in some residual from the input to get the output Y. And this was standard in control theory and signal processing. This came from Kalman in the 1960s. So this has been very, very well studied. And Albert in his thesis kind of figure out how to use these things in deep learning by wiring them up in a particular way, making connections to RNNs and CNNs. And they can work quite well for continuous domains like audio and images, but they haven't worked well for text. And we made a simple modification that allowed it to work really well for text, which is some of these matrices A, B, C, D are no longer parameters. They are dependent on input. And this is very much inspired by attention, where these query, key, and value are projections of the input. And if you make this simple change, actually the model does really, really well. We call this selectivity, but it does completely change the way we have to compute them. Using some of the same idea where this hidden state can be very, very large. So we keep them in SRAM and never write them down. And only the inputs and the matrices A, B, C, and D are written down to HBM. So the hidden state is large. We avoid this memory cost by keeping it in SRAM for the entire computation. So you see that the same trick shows up again, and that allows to train these things efficiently. So I'll show one last result, which is we've done some scaling law experiments comparing Mamba with different model architectures, so the classic transformer, as well as a bunch of other state space or linear attention variants, and also comparing transformer plus plus, which you can think of as the llama architecture, which is a little bit better than the original transformer architecture. And with the scaling law, we're showing the perplexity lower is better. So Mamba is kind of matching the strongest modern transformers. And we train these things. We then take Mamba model trained to 300B tokens and compare it to Pythia, which is trained on the same data set, same number of tokens. And we see that Mamba can match or beat transformers of similar size. So this is validated up to 3B scale. But since then, a bunch of folks have validated to 7B. Some folks from AI21 trained the Jamba model, which is an MOE of size, I think, 52 billion, and that does quite well as well. So the summary is Mamba can match a beat transformer on language modeling. Two key ideas: a selection mechanism and hardware-aware state expansion. And the upshot is we can get better models that scale linearly in sequence length instead of quadratic. But we're still in the early days. I don't think Mamba is kind of the final architecture yet. I think there's still a lot of development. We're starting to understand what the Mamba layer is doing, what attention layer is doing. So this is a very exciting area. So I'll stop here, and I'd like to thank you for your attention.
Work that has brought up like Jamba or Mamba,
Right.
or there's like lots of work
Right.
that combines Mamba with different architecture blocks.
Yes.
So where do you see the future of Mamba? Just could you elaborate more?
Right.
What are your hybrid models?
Yeah, so I love these hybrid models. So hybrid models, you can have actually most of the layers are Mamba layers. You just add in maybe 4 attention layers, and that does amazingly well. So pure Mamba and kind of Transformer plus, they do around the same. But if you take 90% Mamba layers and like 10% attention layer, that does better than the pure models, and that was very surprising. So I think that's very, very promising. So if I have to guess right now what is the strongest architecture, I would say is a hybrid of mostly Mamba layer and maybe 4 attention layers or something like that. That would give you the strongest quality. And that's what some of the experiments we've been running, some of the experiments that other folks have found. So for example, the Jamba model, there's one called Zamba from another company that found kind of similar things. So I think short term, these hybrid models will show up. People will train them because they're strong and they're really efficient at inference. I think longer term, what I'm interested in is trying to understand, okay, we have 4 attention layers that's doing some, that's improving the model quite a bit. Like we want to understand what these are doing. My hypothesis is that these attention layers are acting as a retrieval mechanism. So Mamba layers act as compressing information into a memory, and then attention is doing kind of look up from the prompt. And if once we understand exactly what the attention layers are doing, we can use it. We can use maybe a approximation or some other mechanism, sparse attention and things like that. That will allow us to completely scale linearly instead of still having some layers that scale quadratically. But that's a little bit longer term. I think right now probably hybrid models are really promising. Yeah, great question.
Final, but it's better than RNNs in terms of not like losing information over time, since it's so compressing everything. It's like a fixed state representation. That hasn't been super clear to me, like why it's better. It takes longer to explicitly solve this. Right. Like the KV map, QK, like that. Yeah. Can you give some intuition of why this seems to work?
Yeah, so comparing Mamba to maybe other RNNs like LSTM and GAUs, so Mamba actually has larger state dimension than LSTM. LSTM has the advantage that the recurrence dynamic is nonlinear, so it is more expressive. Mamba you can think of as a linear RNN. So that does mean is not as expressive, but easier to optimize, easier to implement, and easier to make run fast. But one trick we have is that we can make the state much larger, and we call it state expansion. And as long as you design an algorithm that takes advantage of hardware where you don't have to materialize, you don't have to write down this big state, then that's a win. So I would say it's theoretically less expressive, but in practice, because it's a linear RNN, it's easier to optimize, can run faster, and we use this state expansion thing to essentially have more capacity to remember. Yeah. These are all great questions.
If that's the case, doesn't it change the reality?
Right. Yeah, that's a great question. Yes, we do expect to have larger state for longer sequence. It just makes sense. If you read a longer article, like you want to remember more stuff. So far the state expansion has been at a constant factor of 16 or so. So like you use 16 bytes per layer to store. So you can compress it. You can think of it as like equivalent to a KV cache of you only store like 16 tokens, but the model kind of figures out like what information should I put in 16 slots. If you go longer sequences, you might need to scale to like 128 or something. We have some good positive experiments there. Yeah, so it's not quite clear, but we've seen 128 being quite good for really long sequences. And we've seen a lot of work on the transformer compression side where things like local attention also works well, and local attention in some sense also kind of fixed size state. Or if you do like the sparse or low rank, then you also kind of reduce the size of the state. So I think the KV cache as written probably is like too big for what we need. I don't know exactly, is it going to be exactly linear? Is it like n log n? I have no idea. But this direction does seem promising. And I think it's convergence of a line of work on attention approximation and state space. Yeah. Great question.
Thank you, speakers. Since we are below.
Right. Thank you.
we go to our first paper session, and our first paper presenter is going to be Yuval Stoichwik. The paper is towards greener LLMs, bringing energy efficiency to the forefront of LLM inference.
Hello, everyone. I'm Jovan. I'm a PhD student at University of Illinois at Urbana-Champaign, and today I'll present you our work in collaboration with UIUC and Microsoft Azure Research towards greener LLMs, bringing energy efficiency to the forefront of LLM inference. So we are witnessing that nowadays LLMs are emerging software in data centers. The modern generative large language models are tuning ubiquitous in their use cases, leading to their large-scale deployments in data centers. So we can see that Microsoft Azure, Google Cloud, IBM Cloud, they all have LLM service offerings that their users can query. We can see that LLMs can be used for chatting, such as ChatGPT, content creation, language translation, or programming using GitHub Copilot. So generative LLM inference is predominantly built upon transformer architecture, meaning that we have many layers of which we have attention mechanisms plus multi-layer perception, and they can be of different flavors. They can be encoder only, or encoder-decoder models. However, all of them follow more or less the similar flaw, such that users will submit their prompts or their request, and then it will go through multiple iterations until we reach to the end of our inference. So in this case, we submit a prompt. In the first iteration, which is called a prompt generation phase, we will take all the inputs in this prompt, all the tokens, compute them in parallel to get the first output token. Then every other iteration, which is called the decode phase, we will take the lastly generated token and the key value cache, which stores the previously computed tokens, and compute the next token. The difference between the prompt and token generation phase is that prompt phase is compute bound. We have many tokens executing in parallel, while the decode phase has only one token, but it has lots of memory, so it is not compute. Instead, it is memory bandwidth bound. So far, we saw that large language models can be improved with different techniques such as quantization, parallelization, changing the algorithms. But how that affects the energy consumption? The LLMs are running on power-hungry GPUs, which means that the energy consumption of data centers is skyrocketing, leading to the point that we have the energy wall, and it prevents from further expansion of data centers. So lots of work was done on improving the performance, scalability, and accuracy, but what about the energy consumption? We observed that the energy efficiency of LLM systems is not explored, and in order to make it truly ubiquitous, we need to put this puzzle as well in our systems. So we observed that LLM inference workloads have new challenges that were not seen before with previous data center applications. First, as LLM inference is similar to other user-facing applications, it has variable loads, meaning that we have periods of low load and then some bursts of requests that we have high load. However, the request variation is also very different. So some requests can be very large with very large inputs. The other requests can have very short inputs. Some we can have a long outputs, while others will have only a few token generation phases. And finally, there are many configurations or knobs that can impact both performance and energy efficiency of LLM workloads. So how the GPU frequency, model parallelism, batch size, and how many model instances we need to serve the LLM so that we get the acceptable performance while minimizing the energy consumption. So in order to meet the demands from the performance perspective, but also to make it sustainable, with the first step we need to do is to perform a thorough characterization of the environment. And this is exactly what we do in this work. We take, in these specific examples that I will show, we take the Llama 2 model with 70 billion parameters. However, we experiment with other models such as Bloom and observe similar trends. We take the VLLM as state-of-the-art serving platform, but we also confirm that the other serving systems such as faster transformers have the same properties. And we run everything on NVIDIA H100 machines with GPU frequencies going from 800 to 800 megahertz to almost 2 gigahertz in steps of 200 megahertz. And we care about the SLOs for time to first token and time between tokens. We set them to be 5 times of their execution time on an unloaded system. So first, let's see how the GPU frequency impacts both performance and energy efficiency. Here, we show what is the normalized time to first token with different request types. We group the request into short and long inputs and outputs, short, medium, and long inputs and outputs, depending on the size of their input tokens and how many generation phases they have. And then we run our inference with different frequencies from 800 megahertz to 2 gigahertz. We can see that for different request types, the impact of a GPU frequency is very different. So for medium, if we have larger inputs, because this is a compute-bound phase, higher frequencies will help keep the performance high. However, when we go to very large inputs, if we run everything at high GPU frequencies, we run into power capping events, which further reduce the performance. So that's why you can see the impact of frequency is going from short to medium inputs. We get higher impact from frequency, but once we go to the large inputs, the impact of frequency diminishes because of the power capping events. So here you can see that the power consumption across different input and output types with different frequencies. And as I said, because we have the power capping events with large inputs, even if we're running from 1.8 or 1.6 gigahertz, the power is the same because of the power capping events, trying to keep the power consumption of our GPU below the value that it can support. On the other hand, the energy consumption is unclear and it's not linear as performance and power consumption. So we can see that as we reduce the frequency, we reduce the power consumption, but we also increase the time that our LLM inference will take. So then the energy consumption will get some sweet spot at the different frequencies depending on the request types. Therefore, our first observation is that optimal GPU frequency will depend on the SLO, meaning how much performance we are willing to trade, and also on the request type. So different requests will have different optimal energy performance trade-off. Second thing we explore is the request batching. So we group multiple requests together in a batch and process them in parallel. And we use both continuous and mixed batching, meaning that we schedule everything after each iteration, but also we make decisions so that we combine in the same batch both inputs and outputs, meaning prompt and token phase. So the batch size intuitively can impact the performance. So we take here different batch sizes, meaning how many requests we combine. And these graphs are all for the medium-sized inputs and medium-sized outputs. And we see what is the performance impact as we change the frequency with different batch sizes. So we can see that as the batch increases, the frequency impact diminishes. Again, as we have larger batches and more things to compute in parallel, higher frequencies will lead to more frequent power capping events, so that we will execute into lower frequency domains. Similarly, as we have larger batches, the throughput of our system will be higher because we can process many things in parallel. However, again, the energy consumption of our system will depend on both what is the batch size and what is the frequency we select. So it will not be neither linear, it will not neither decrease nor increase linearly. It will depend on the load of the system and on our SLO. So the second observation we make is that we need to dynamically set the optimal batch size depending on the system load. It will change as we have lower or higher loads and what is the expected performance that we want to achieve. And finally, we explore the model parallelism, meaning that in order to improve the performance and allow the execution of models that cannot fit a single device, we can split the model into multiple devices, either through tensor or pipeline parallelism, or in a combination of the two. So tensor parallelism means that we will take a single layer, split into multiple sublayers, and then execute in parallel on different GPUs, and we will aggregate the results across them. While pipeline parallelism means that we will split multiple sequential layers and execute them on different devices sequentially. So the model parallelism strategy definitely influences the performance. Here we show what is the maximum throughput we can achieve with tensor parallelism 2, 4, and 8 as we change the frequency of our system. However, what was not explored before is that the model parallelism can also influence the energy consumption. So we can see here that What is the normalized energy consumption? Everything is normalized to the tensor parallelism 8 at the highest frequency. What will be the consumption as we change both frequency and parallelization strategy? We observe that the optimal model parallelism will depend both on the load type, both on the current load and on the request types. So we want to keep the performance high again, but we want to meet the sustainability impact so that we minimize the energy consumption. So our characterization asks a question how to design LLM inference systems for energy efficiency. We observe that we have available knobs such as GPU frequency, model parallelism, batch size. However, for our optimization function, in order to get the optimal energy consumption while meeting performance, we need to take into account request type, load of the service, and the SLO that is expected for this application. Therefore, in the future, people will need to work on scheduling, placement, auto-configuration techniques in order to balance between the performance and energy trade-offs for LLM inference workloads. To conclude, in this work, we perform the characterization of the impact of energy efficiency knobs on various levers available in modern LLM inference systems. We get insights in difference between the performance optimized and energy optimized designs, and we take into account these platform decisions that can be made towards the truly energy efficient LLM inference workloads. We believe that in this way, we can pave the way for the orchestration plus cluster and node level scheduling work with more holistic optimization functions. Thank you for your attention.
Explain what happened, I mean, behind this change. If we want to look into they have like software level of optimization, hardware level of optimization when they fetch the data or do the pad. So how you gonna explain and analyze why we have something like this?
Yes, so why it's not linear? First, because the energy is product of power and the execution time, like how long do we operate in a specific power domain. So as we reduce the frequency, for example, the power will be lower, but the execution time will be higher. So we need to find the sweet spot that will get the minimal execution time multiplied by the power. So also here, we cannot always blindly choose the sweet spot because it will depend on the SLO. For example, in this case, the energy may be minimal, but maybe the performance will not be acceptable. So we will need to have a more holistic way into what is the performance plus what is the energy. And the energy, in our opinion, we need to do some profiling steps like this and then use this as inputs for our optimization functions. Yes.
Of the energy and the performance.
Yeah, it definitely needs to be very dynamic. Yes, it will depend on the load, it will depend on the inputs, and it will depend on many other things that are known only in the runtime. Yeah. So this is average, yes.
Our next presenter is Stephen Barnes, which we'll be talking about. We combine neurosymbolic AI by workload characterization and cross-layer co-design.
Awesome. Thanks. Good morning, everyone. I'm Zixuan. I'm a PhD student from Georgia Tech, working with Professor Arijit Rochesbury and Tushar Krishna. And today it's my great honor to be here to present some of our recent work on the neurosymbolic AI. So the title of my presentation is the Demystifying Neurosymbolic AI, where workload characterizations and software hardware co-design. So before I start, I want to thank my alumni, advisors, and collaborators to contribute to this work. So this is the quick summary of my talk. So the goal of our work is to try to understand the neurosymbolic workloads from architecture and system perspective, and try to identify the potential inefficiency reasons for this kind of algorithms, and also try to optimize the efficiency and scalabilities of that through this co-design methodology. So before we delve into the technical details, so first let's say what is neurosymbolic AI. So neurosymbolic AI basically is trying to integrate both the neural network and some symbolic AI approach. So the neural network we know is very good at to extract the features and is good at some flexibility stuff. And for symbolic AI is good at some to explain the things to based on some rich high-level representations of the real world. So the neurosymbolic AI try to bridge these two stuff to leverage the benefits of both neural network and also the symbolic AI towards some cognitive and trustworthy AI systems. So just a very naive examples. So here we use Apple as examples. We know this is how neural network works. And for symbolic AIs, usually we know some knowledge and information about the apples, and we do some reasonings about this object. And here's another example. Say we have a visual reasoning task. So here we give you our pictures and we also ask you questions. And so say for these pictures, we ask are there equal numbers of large things and metal spheres. So how we as a human to do this task. So we first read the questions and then to check the pictures, and then we say, hey, there's three large things. And then we also check the pictures. We say, hey, there's three metal spheres spheres. And then we use our logical reasoning capabilities to think, oh, the number of these tools are the equal. So the answer is yes. So if you look at this task, so basically we have this question understanding task, and we have this visual perception, and also we will use our logical reasoning to do this kind of task. And this is a high-level pipeline, so don't worry about details. So basically, if we pack the algorithm, we see we have some vision task and some structured representations, and some also language task, and then to convert them into some symbolic operations to do this cognitive task. And some recent examples, this is earlier this year from Google DeepMind. They have this alpha geometry stuff, which they use the neural symbolic approach to solve some Olympic level math problems. So basically, they use this large language models or neural network to generate some construct, and then used a symbolic approach to do the reasoning underlying rules of these math problems. So you can see, I apologize for some format issues on the slide. So you can see for GPTs cannot solve this kind of a task, but for this alpha geometry with neural symbolic approach, we can reason the rules behind that and can reach the human level, the gold medalist level of this math capabilities. And that is also similar to our human mind thought. So for us, we have two minds that were we have the fast to give us some initiative and fast thoughts, and also we have some slow thoughts to make some rational decision making. So the fast is more like a neural network, and the slow thought is more like a symbolic reasoning stuff. So the so the talk, so the agenda of my talk is we try to categorize these different neural symbolic workloads and to identify some potential inefficiency reasons, and also try to optimize that through some co-design approach. So for the first part, we'll quickly show some workload characterizations and identify some efficiency reasons. So first, we check a bunch of different neural symbolic algorithms, and we find based on how this neural and symbolic interact with each other, we can roughly categorize different algorithms into these different domains. So we can have the neural network within the symbolic, or we can also have the symbolic within the neural network, or where we can pipeline them each other. So we have these different categories, and then we also try to pick some representative neural symbolic workloads and do some workload profiling. So here we pick 7 workloads, And here we just give a high-level intuition what this workload looks like. So here is the neurosymbolic, one of the neurosymbolic workloads, which we try to solve this spatial temporal reasoning task. So we have we give you a 0 cross 3 image, and we give you the first 8 image, and we try to, based on the patterns and underlying rules, to guess what's the nice one. So you can see for this neurosymbolic approach, we will first use the neural network to do some of the perception, to do visual perception, and then we will use this symbolic reasoning to understand what's the underlying rules behind that and guess the final result. So it's turns out if we use a GPT-4 for this kind of task, the accuracy is around 86%. But if we use this neurosymbolic approach, it can reach 98% accuracy. So we pick this a different type of algorithms belong to different categories and work for different applications. So some key I want to highlight some key profiling observations here. So first is we profile these different workloads on the CPU plus GPU architectures. You can see the x-axis is different workload and y-axis is their runtime percentage. So what we find is that compared to a pure neural network, the neurosymbolic method it has a kind of a long latency compared to the neural method, especially for the green part, which is symbolic, which is sometimes can become the system bottleneck, which is run not very efficient on the CPU and GPUs. And we also try on the different across the hardware of the different skills from both the edge and workstation. So we have these consistent observations that symbolic is not efficient. And then we do some in-depth compute operators, which we try to understand what's the operators inside this workload. So you can see on the y-axis, we divide these workload operators into these different categories. And on the x-axis is way to look into both the neural and symbolic of each workload. And the numbers here shows the runtime percentage of each compute operators. So the high-level takeaways here is we know a neural network is not surprised that is dominated by these matrix multiplications and convolutions, and we find out that this symbolic is mostly dominated by some vectors, element-wise operations, and also some logical operations. And because we have this neural and symbolic, they may integrate with each other in the different ways. So the control flow is also very complex for this kind of workloads. And so then we'll try to understand why the hardware is not efficient for this type of workload. So we use some inside compute, inside profiling, this kind of tools. And the key takeaway here, apologize guys for the format. So the key takeaway here is we find that the symbolic operations has very low ALU utilizations and also very low cache hit rate, and also very high data movement between the CPU and GPU. So resulting in the low hardware utilizations and also the inefficiency. And then we also try to do some root flow analysis. So and we find that the symbolic operations is mostly the memory bound. And here, because of neural net is more like the ConvNet, so it's more compute bound. So this is a quick summary of what our profiling insight of the both neural network and neurosymbolic. So we find compared to the neural network, the neurosymbolic approach features a heterogeneous workloads that both the neural and symbolic. And for the hardware efficiency, the symbolic is not very efficient because of the low utilizations and low cache rate. And also the symbolic is like memory bound and also have the complex control flows. And also we also look into this sparsity, we found that it has a various degree of the sparsity. And in the second part, I will just given time, I will just show a high-level overview of how we optimize this neurosymbolic system through this co-design approach. So here we build SoC architectures, have both the host SoC DRAM and also these neurosymbolic accelerators. So some key features of our design is that based on our profiling result, we design some P processing element that is reconfigurable to both the neural network and the symbolic. So basically we can use the existences of arrays and the P architectures, which can enable it to support some of the symbolic operations. And also with some spatial temporal mapping, data flow, and scheduling to adaptive schedule this neural and symbolic components. We can happy to discuss more in the poster session about that. And looking ahead, what we are working on right now is we are trying to integrate these large language models plus the neurosymbolic. So basically we use these large language models for these generations, idea generations, and also for the symbolic for this test and critics, and for some reasoning tasks. So through that combinations, we think we try to improve the a human moral judgment, some conversational reasoning, and some and also the scientific computing capabilities. So with that, quickly summary. So we feel this neurosymbolic is one of a promising paradigms towards the cognitive AI systems, whereas not very efficient on this off-the-shelf hardware. So the approach we take is we first to do some workload categorizations for this different workload and identify the inefficiency reasons and propose some optimization method. And for now, we are deeper our understanding for this different workload and trying to explore this large language model plus neurosymbolic for that. With that, I want to thank you all for your attention, and I'm happy to take any questions if you have time. Thanks. Yeah, that's a great question. So for now, we haven't explored FPGA for that, but we think that FPGA is a variable candidate for this neurosymbolic approach, because the essentially we think for this neurosymbolic architectures, we still need these neural network accelerators, these architectures, but we can add some of the symbolic accelerators on this neural network. So we think that FPGA could be one option, and actually we are exploring that for now. So yeah, thank you. Thank you.
Our next presentation is flash attention stable, and the speaker is Alicia Golden.
Great. Hello, everyone. My name is Alicia Golden, and I'm going to be presenting our work, Is Flash Attention Stable? With collaboration from others at Harvard and also at Meta. So as machine learning becomes more and more complex, training these large models is ever more compute and resource intensive. Especially with the advent of LLMs and generative AI, new state-of-the-art ML models often take months to train, with Meta's new Llama 2 model, for example, taking over 1.7 million GPU hours to train. And with this GPU training time in such high demand, any disruptions to the training process can be both a big disruption and costly. However, recently we've seen these increasing reports of instabilities during training, which often take the form of loss spikes. And so, for example, shown here is a training curve done by Mollyberg et al. At Meta, where they observe these different spikes, in fact, happen 29 times throughout the course of training. And others have observed similar things, such as at Google in the training of their PaLM model. And so these loss spikes often cause training to stop, you have to reset, and then start again, and they can be very disruptive in terms of the resources and the GPUs that are in such high demand. However, training instability is a challenging problem to study, and its causes are largely unknown. So current working hypotheses, for example, say it might be due to a specific optimizer, such as the Atom optimizer during training. It could be due to bad data or some combination of bad data and a particular model state, or it could be due to numeric deviation from specific training optimizations, such that the gradual accumulation of error eventually accumulates and results in a spike. And so in particular, this numeric deviation is difficult to quantify. because training is inherently stochastic, so some level of deviation might be acceptable, but determining where that threshold is for where it becomes unstable is a challenging problem. And so in this work, we focus in on numeric deviation as a potential cause of training instability. And we really aim to develop a principled and quantitative approach to analyzing numeric deviation across different training optimizations. And so more specifically, the question we aim to address is, can we develop a principled analysis to not only quantify, but also contextualize the impact of training optimizations on numeric deviation? And as a case study, we use the widely adopted flash attention algorithm that we heard from Tri earlier, and we try to investigate its potential for numeric deviation. And so in the remainder of this talk, I'll do a quick introduction to flash attention. I'll outline our experimental methodology and then dive into some of our results, including 1, quantifying, and 2, contextualizing this numeric deviation before going into a discussion of some future work. And so as we heard from Tri earlier, attention is a true bottleneck in these transformer algorithms, and it mainly results from this quadratic scaling with sequence length. And so the widely adopted flash attention algorithm essentially aims to break this sequence length scaling dependency by using both tiling and recomputation. So essentially computing this n by n similarity matrix block by block, such that each block is small enough to fit inside SRAM, and you can reduce the amount of time that you need and accesses to HBM, which speeds up the attention process. And in order to make this work, flash attention introduces this notion of rescaling factors. Because when you're computing this matrix block by block, you need, in order to compute the true output, you need to know all the values of that matrix a priori. And so we don't have this in our blockwise computation, so we do some additional rescaling or normalization factors for that softmax. And so the question that this arises is, if we have these additional rescaling factors, could this be a potential source of numeric deviation, which could have later downstream impacts? And so to investigate this, we take a two-pronged approach where we first design a micro benchmark to isolate the impact of numeric deviation on a single forward pass. And then secondly, we contextualize this observed deviation within the context of model training to try to see whether this really has an impact on downstream model weights. And so diving into the first part, we essentially construct this benchmark where we take in the same query key and value vectors, and we compare the output of the attention matrix, whether we're computing with baseline or flash attention. And we re-implement the flash attention algorithm to essentially break open the black box of the CUDA implementation or SDPA call and allow us to kind of perturb the algorithm to adjust the amount of rescaling that is happening and measure that impact, and also change the number format that is being used. So flash attention works with BF16 and FP16, but we wanted to extend this to other number formats as well. And so this shows some of our initial results on measuring the deviation in flash attention. So you can see on the y-axis, we are measuring the maximum difference between the attention matrix outputs, and we sweep across different number formats. And so we can see that there does exist some slight numeric deviation between flash attention and baseline attention. And as we have number formats with fewer Mantis bits, this deviation increases, like at BF16. And the question becomes, is this deviation significant? Is this significant downstream? And so we first run a set of additional experiments to try to isolate whether this is coming from the pure number format or whether it's coming from flash and baseline attention. And so we compare each of a series of experiments to a baseline value. So we say, okay, a golden value is at one of the highest number formats, FP64, using baseline attention. If we count that as the true value, what is the deviation for all these different methods? And so there's a lot to analyze here, but I want to focus your attention on this first bar, where the red is baseline attention, the blue is flash attention, and we measure that deviation as compared to that golden value of FP64 at baseline. And we find that flash attention sees about 10 times more numeric deviation than baseline attention at this point. And so in our paper, we additionally run a bunch of experiments trying to adjust the amount of rescaling factors. For example, we look at larger block sizes and find that that leads to less of this deviation. So please come talk to me at the poster session if you're interested in hearing more about that. But for the context of this talk, I wanted to focus in on this question of if this deviation is significant. And so the second part of this is contextualizing it within model training. And so to do this, we measure the model weights and how they deviate throughout the course of training incrementally using these two metrics. So we use the maximum difference between the weight tensors as sort of an upper bound. And we also use Wasserstein distance, which gives us a sense of the value distribution of the tensors. And our initial measurements on how model weights change throughout training suggest that the distance is increasing, meaning the models are diverging throughout the course of training if you train one with baseline and one with flash attention. But training, again, different model weights could lead to similar downstream performance. And so we wanted to kind of be able to get a relative sense of if these weight changes are significant. And so we compare against several other known training optimizations. So for example, here we show models trained both at baseline attention, one with FP16 and one with FP32 number precisions. And we also run some additional experiments looking at FP16 versus BF16 and even random model initializations, which are in blue. And we find that the red curve of the weight changes of flash versus baseline attention, all the other optimizations kind of serve as an upper bound for this, suggesting that the flash versus baseline attention weight changes is actually 2 to 5 times less deviation as compared to this low precision training. And so this kind of brings us back to the question of, is flash attention stable? And we've been able to look at this kind of principled numeric analysis to quantify the weights and then also give us a relative metric of how these weights change without training entirely measuring downstream accuracy, but kind of a closer proxy in order to see whether these weight changes are significant. But in order to kind of fully make this link back, there's still more work that needs to be done, in particular, in between this link of numeric deviation and training instability. But nevertheless, our numeric quantification methodology really opens up a broader set of questions in terms of other training optimizations, what deviations that they could produce. And so in future work, we hope to extend this to other training methods and see and kind of measure their deviation. And throughout this process, we've really learned a lot about training instability, and it really raises a lot of interesting questions in this space. So there's a lot of interesting questions at the intersection of training instability and reliability, such as the causes of different hardware failures, looking at the system overhead, so the amount of queuing and requeuing time that results when you have these spikes and disruptions in training is also very interesting. And when you have these loss spikes, you often see power surges across the data center as well. So this has sustainability aspects as well. So there's a lot of interesting questions in this space, and it's very exciting. So hopefully by sharing our methodology, we can encourage others to also investigate these types of questions. So thank you so much for listening, and happy to take any questions.
I saw your graph, the B floating 16's performance worse, like more degradation than floating by 16. What's your insight behind it?
Yeah, so we find that, right, at different number formats, so BF16 has like fewer manticipants in the number format, so there might be more approximation that's happening with these additional rescaling factors. And so it's small rescaling of like recomputing the value instead of just knowing the output value a priori. And so we were trying to investigate whether that small deviation is significant. And in downstream training, it's not as significant as we might have originally guessed, but it's this kind of process that we're trying to share of how to determine whether these deviations have impact downstream. Yeah, exactly. So we performed like at FP64 floating point value, which is where our benchmark came in. And we measured just baseline attention. That was our golden value. And then we did baseline attention at each of those number formats and flash attention at each number format.
So with P16, BF16, like what will happen to train a little bit longer because it is faster. So we afterwards see some stability. Like, is it like worth still going there and then maybe train longer and resolve some of the problems, or that's not.
Yeah, so no, that's a really good question. And I think, yes, kind of like that downstream longer impact is really interesting to investigate. And so these models take a really long time to train. So kind of getting this like initial estimation of whether the weights are significant is what we were trying to address. But yes, like going further downstream would also be an interesting question.
Take a 12-minute break. We are a few minutes behind schedule, so we'll reconvene at 10:30 and try to start the session properly. See you all at 10:30.
What would you need?
If you need a pointer, the pointer still
Sure.
works.
Thanks.
We are ready to start with our next session. Our next speaker is Amir Yashanpal. We received this PhD degree from Georgia Tech. His work was recognized by leaders from Microsoft. He's currently a research scientist at Google DeepMind, where he is working at the intersection of machine learning and computer architecture. His work applies novel ML techniques to better design hardware accelerators. He's also interested in designing large-scale distributed systems for training and applications, and has led the development of a reinforcement learning system that applies to the TPU board that efficiently manages thousands of activities of complex data. Amir also knows some helicopter code design, shaping the future generations of ML accelerators.
Yes, I can. Thanks for the introduction. Good morning, everyone. Thanks for the introduction. So today I'm going to talk about, the title can be a little bit misleading. It's about using machine learning for designing accelerators. But I hope that I can cover two different design points that we use machine learning effectively at Google. Okay. Let's see. Okay. So I think all of you have seen this graph over and over. It's about 42 years of process data, and it seems we are reaching at the point that we cannot take more juice out of transistor. And we have to think out of the box and see how we can kind of sustain the performance improvement that we used to have. I think I don't need to emphasize that over the past couple of years, I think past year, we have seen a tremendous number of machine learning technologies like ChatGPT, Bard, or Gemini recently they call it. And actually, this is a funny meme that they created from our CEO. I hope I can present it.
AI, generative AI, generative AI, generative AI, AI is AI, 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 AI. It uses AI to bring AI, 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 AI.
Okay. I think I can convince you that how important AI is for our kind of company. Okay. Let's see. So yeah, I mentioned that we are reaching to a point that room at the bottom or transistor level plateaus, and we have to think out of the box and try to see how we can kind of further improve the our system. So it seems there are a lot of opportunities at the top, and I will explain what do I mean by at the top. And there are we can use generative AI to further improve the performance of our systems. So this is a really good write-up from Charles, and they talked about this room at the top. And they talked that there are a lot of opportunities across the software stack from algorithm and hardware architecture. And this is kind of my note is that in Moore's law veins, innovation paves different paths. And we have to think about how we can kind of take juice out of these opportunities on the top of the stack. And this work, I'm going to talk about two aspects of our work on the hardware architecture that we use machine learning. And a little bit, if I have time, I will talk about how we can use machine learning to kind of optimize software and algorithms. So let's start with the first part, hardware accelerator. This is a work that we published like 2 years ago. And the goal is that how can we use data, a tremendous amount of data that we have, to optimize the design of hardware accelerators. So let's start with the objective. What is our objective here? Our objective here is that we want to generate a hardware accelerator, which is specialized toward one or a set of applications, machine learning applications that can, for example, we want to design a hardware that can run mobile net or recently LLM models very efficiently and very fast. But there is a lot of challenges here for this design. First of all, in the domain of accelerator, there are a lot of invisible points. And those invisible points stem from various challenges. For example, you cannot realize your design on the hardware, or compiler is not ready. Here you can see a lot of these black dots here. These are all invisible design points. And if you want to use like traditional machine learning algorithms that are optimized for
kind of continuous optimization, it would be it would be challenging. On top of that, when we want to design accelerator, you need to meet some design constraint. And there are many, many design constraints: area budget, power budget, computational time. And another constraint is that how can we reuse the data? So we design an accelerator, and then for the next generation, we kind of throw out all the data that we collected and then start over again. Is there any way that we can reuse these data to better optimize the future generation? And lastly, is that how can we develop a kind of machine learning technique or a technique in general to scale favorably with modified design constraint and evolving application? Before we wanted to design something for CNN and now LLM, and who knows what comes next. So let's review what is the typical or conventional simulator-driven or online design. So usually what we have is, especially in the industry, we have a time-consuming cycle-accurate simulations. We go through some optimizer, either human is involved or like some heuristic, and we optimize our model, and then finally we are going to have some optimized hardware accelerator. And this process continues. If the application changes or if the constraint changes, you have to go through this whole process again. What we are proposing, which we call a data-driven offline problem, we want to use the collected data set for our design, whether it's a feasible design or infeasible design. And I will tell you about that, how we can leverage this infeasible design in our optimization problem. And we're hoping to use some machine learning techniques. Don't worry about this conservative. So some learned model that instead of going through this time-consuming cycle-accurate simulation, we use these learned model to iterate fast through this optimization, and hopefully we can get some optimized hardware accelerators. Should I admit these things? Okay. Oh, sorry. So why we are taking this approach? Why do we need offline data-driven techniques? First of all, it's very obvious. It's much faster than the cycle level or cycle accurate simulator that we are using. Instead of like 10 to 11 days, we are just using like a few hours going through this learned model and optimize or suggest solution that may be optimized for our design. And of course, simulation overhead also scales unfavorably for multi-model application. Imagine if you want to optimize your design for many, many applications, you have to go through this simulation path multiple times. Instead, we can use a learned model or machine learning techniques to remove this overhead or mitigate this overhead. The other good aspect of this technique is that neural network generalizes better with immense amount of data. So we talked about data-driven approach. If you have data, whether it's infeasible or feasible, we can use this data to generalize to other data points or other constraints that we have. And this is the kind of a point that I want to kind of highlight, is that when we use the learn technique, even bad data is a good data. And what does it mean? Like even infeasible data point, they can guide you that, hey, these areas is inefficient or it's bad. And you don't want you want the model to learn from these things. I think it is very natural as a human also. It's not like when we see a design that is not optimized, we learn from this. Oh, by the way, this is like I don't know, the cache size is not good, so I have to change my cache size. So this is the point here as well. If we have data, we can use it to train a model which generalizes across different design points. So this is more relevant to this topic of this workshop. We have a Pixel phone, and each of them has this processor, HTPU hardware accelerator. And one of our target was we want to optimize this accelerator because it has a lot of design parameters. We want to optimize this accelerator for a set of applications that we have. I'm not going to go to the details of architecture, but it has a lot of parameters that we need to optimize. Let's talk about our learning techniques and how we use machine learning to optimize our hardware for a set of applications. So let's start from so we define a kind of a loss function. This part is not that important. It's just we use a transformer model because it can generalize better. But the part that I want to emphasize here is about the loss functions that we define. So the first one is actually should be very familiar to all of you, is that we have a set of feasible data points This is the hardware. This is the latency or power or area, whatever it is we want to predict. And we map the input or the configuration that we have to that particular objective. And our goal, for example, in the case of latency, is that we want to reduce the difference between the predicted latency and what is the actual, let's say, or golden model. This is a very natural objective that everyone uses. But these two parts is interesting. Is like how we can use invisible data point. I told you we have a lot of invisible data point and how we can leverage this. So one natural way of using this invisible data point is that we use this invisible data point to push the objective function. For example, in the case of latency, we want to say that these invisible points are not favorable, are not good for our search. And this is the way that we tell the model that avoid those areas. And the last part is about adversarial example mining. If you're familiar with a generative adversarial model, this is a very similar phenomenon. I will try to kind of explain it, why we use this adversarial network. The goal of this loss function is to avoid overfitting on the current data. So how we use it in the optimization loop, we train a model and we use this optimizer to suggest some data points, okay? And then during our training, we are saying that these data points are not also favorable. It's a little bit contradictory to kind of, if you think about it, but our goal here is to avoid overfitting on whatever optimizer is suggesting. And it seems that it would, adding this loss function is very productive in avoiding overfitting and helps the model to generalize better to unseen data points. So let's look at some of the data. This one is a little bit. So the first one is that we want to design an accelerator for new unseen application or in a zero-shot manner without any optimization. So you have the data, you go to your model and say suggest a design point without any further fine-tuning. I want to kind of add a disclaimer here. When people talked about unseen data, still the application is within the same distribution of the previous application that it's not like completely different thing. It's unreasonable to expect a machine learning can kind of generalize to something that we've never seen and it's out of distribution. Still, if you look at the application that we have, they are still in the realm of CNN, RNN, and same distribution I would like to highlight. Okay, let's go through the results a little bit. So we have a different kind of scenarios. First, on the train application is how we train our model. So we use some data from MobileNet V2, V3, and different models, and we train our model. And during the test, we are completely using a different model, for example. So for example, in this case, we train on HCPU and V3, and instead we are using V2. We have also some area constraint, and we are comparing our scenario between evolutionary or online and what Prime suggested, basically. As you can see, in most cases, Prime, which is our approach, provide better design points compared to evolutionary online algorithm. And I don't need to remind you, evolutionary online algorithm still requires to go to the simulator and go through that tedious process. So another thing that we wanted to kind of explore is that if we want to do extreme specialization, let's say we want to design one accelerator that is extremely optimized for one particular application, and we wanted to see how our model kind of behave in these scenarios. Again, like there are a lot of data, I'm not going to go through them, but we show that like our technique provides like 2.69 speed up over the current or that generation of pixel accelerator while reducing chip area by almost 50% across a range of applications. To summarize this part, we kind of showed a scenario that you can use data, not only physical data, but also invisible data point to train a model that can generalize well across a range of application and across range of hardware designs. So we had a couple of other follow-up work on this topic on how we can use machine learning. The first work was about how can we use graph neural network for throughput estimation. And we talked about also like using some prediction for HTPU. And finally, we proposed something for how we can co-design our machine learning model and accelerators. If you are interested, I would kind of recommend you to go check them out. I have 15 more minutes. Okay, correct? Okay, perfect. Okay, this is the work that I'm very interested. So we talked about how we can use machine learning for hardware. This work is about how we can use machine learning to optimize software. You can imagine like if you have a C++ code and you write it as a kind of bad programmer, which I am, I write my code. And when I want to scale it up and run it on the kind of data center or even like Pixel phone, I want the design to be optimized. But usually it takes me hours or days and going through many tools and many kind of profiler to make sure that the code optimizes. So here, what we want to answer is, can we use, sorry, I want to use this. Oh, okay. So before getting into the technique, I want to kind of motivate that why such a problem is important. Code optimization is very important, especially if you run it at a scale. And however, it's very challenging for machine learning to optimize it. Why it is important? Because it has a practical implication and of course, environmental impact. If your code is not optimized and run it at a scale, you're burning a lot of CO2 and energy and so on and so forth. However, when you want to do code optimization, as I mentioned, you need to reason, you require intensive reasoning skill. You have to understand what is happening on the hardware, how should I change my cache line, what is this profiler, and a lot of process to make sure that your code is optimized for your target system. And of course, in the machine learning community, because it's a hard problem, and usually we don't have a benchmark for it, it's generally an underexplored theme in the machine learning community. So, of course, inspired by all this LLM and AI, we wanted to answer this question of whether we can use machine learning and particularly LLM to perform program optimization. So here we have a kind of very simple example is that if I ask myself to write a code that do this addition of the integer number, I probably write a for loop. And we want to see if we can ask a neural network to change this and perform a completely kind of closed form solution, which doesn't require any loop. And it's more optimized compared to the code, the original code. So you might ask, why do we need machine learning? I mean, there are a lot of tools, there are a lot of things that can do this for us. The next best tool that you can think of is compiler optimization. However, compiler optimization, in terms of type of optimization that they can perform and the scale of transformation that they can perform, they are very limited. And another part you might think as, okay, there are like program synthesis or formal methods, but those also does not scale compared to machine learning techniques. Okay, so far it's very cool. We can use it, awesome, but it's not there yet. So, however, if we want to use machine learning, we need a proper benchmarking and a proper setup to teach the machine learning model that, hey, this code is optimized, this code is slow, and so on and so forth. And evaluating these program optimization in general is very challenging topic. And why it is the case? If you have a code and you want to kind of measure the timing, sure, you can do the timeout, time it, and everything. But if you want to isolate your program and understand, okay, in terms of algorithmic efficiency, what is my code is doing compared to another version of my code, usually there is a lot of variance in the measuring the time. And of course, if you change your hardware, you might get a completely different problem. And it is very hard to teach the machine learning to deal with these variances. So we're going to deal with a lot of false positives. For example, if the same code in one hardware or in one scenario, which is busy CPU, might give you a different time compared to an idle CPU. I think I already mentioned that if you switch to a different platform, you might get inconsistent measurement. And it is very hard to teach the model to deal with all these inconsistencies. So our solution was very simple. Hey, let's use simulated CPU. Let's use Gem5, for example, to deal with this inconsistency and variance in the code. So if you use CPU, which any simulator, CPU simulator, in all scenarios, even if you have a busy CPU, if you have an idle CPU, if we are using a completely different platform, we get a consistent measurement, and that's exactly what we want. We want to isolate the optimization so we can teach the model where to focus and what to learn. I think I'm going to skip this. We use Gem5. It's detailed simulator, and I think most of you are familiar with it. Okay, so we talked about the measuring the performance of code, but now let's talk about the data set. How we can collect the data set that shows us the different optimization that people perform on the code. Gladly, there is like a competitive programming, and we use that data set as well. It's available online. So what is the competitive programming? And let's go through the process. So you have a problem description, maximum subarray of a sum, let's say. And as a programmer, you start with a version of your code. Maybe first version is not working or is not optimal. You kind of get some feedback, and then you optimize your code because you have a deadline as well, like you have a timeout. You optimize your code and create another version. And this is the iterative process. And I think all of us programmer, we are deal with this, right? So we optimize and optimize, go through this loop. So the competitive programming dataset has all this history for each programmer, has all these version of programs that they go through for optimization. So we collect this and create like 77K training and 1K unique tested for this set of problems. So different version for the same user. Okay, I'm going to skip a little bit. So we have a couple of metrics of interest for us. So one is the percentage of optimization. We want to understand across our unit test, what percentage of the programs we can optimize or the machine learning can optimize. Another metric that is important is about a speed up. We want to see how much machine learning or generated code optimize the original, optimize the slow code. And finally, about correctness. We want to ensure that what percentage of the generated code is correct compared to human evaluation. Okay. The first thing, we go to the LLM and ask LLM, can you optimize the code without any technique, without any fine tuning or anything? But it turns out pre-trained LLMs struggle to optimize program. So this is a very simple case. We have a basic instruction, given the program below, improve its performance. And this is the slow version, and we are hoping the model to generate an optimized code for us. There are other scenarios. You can use few shot prompting or so on and so forth, and or like chain of thought. But it seems that even with these kind of optimized, even with this advanced method of prompting a LLM, it's still the model struggle to optimize code. This is a lot of data. I'm going to kind of give you the snapshot summary. So we tried different models. It is just a snapshot of the model. Code Llama, which is optimized for code, GPT-3 and 4. And we have a human reference as well. Human reference is the one that people actually iteratively optimize it. As you can see, the model usually struggle to reach to the human level optimization. And they're actually very suboptimal compared to what human does. And this is not ideal. We don't want that. So we came up with some techniques to close this gap between human speed up and what model can offer us. So there are two techniques that I'm going to talk about, if I have time, about retrieval and then about the fine tuning. So let's back to how human actually codes. So usually, at least what I do is when I see a problem or when I see a code, I create some similarity. I say, okay, I have seen this code before, or this is how I can optimize the code. Let's do the same thing for machine learning or LLM. It's not like a very advanced technique, but it's a kind of very intuitive for a human developer. So we did the same thing. We get the slow code. We use the BERT model to score each program in terms of similarity. And we have our database. We say, okay, this is the slow code. I have my database. Select top 2-3 program that is similar to this code. And instead of feeding only one sample to the model, we feed the slow code and some of the similar code. This is how people optimized code that is similar to this. And it turns out that retrieval-based program optimization can be very effective in terms of teaching the model or prompting the model how to optimize the code. So we use like different version, like use random examples, so it seems it's not optimized, but we use also this BERT score that helps us to improve the program. So this is how it's going to be done. So it's a similar, so this is our target program that we want to optimize. And instead of only giving this to the program, we add some similar program as well. So this is the similar code, this is how this is optimized, and multiple examples. And then later, we ask the LLM to give us the optimized version. A lot of examples here. I'm not going to talk about them. So let's review some of these models when we use this retrieval technique. So Code Llama is a very small model. It still improves, but not as much as the human optimization. But it seems models like GPT-4, it's very, very effective in terms of improving the performance of the code when you use this retrieval technique. Let's talk a little bit about fine-tuning as well. So when we talked about fine-tuning, we came up also with some techniques that make sure that the model can utilize this collected data and how we do this fine-tuning. First of all, naive fine-tuning in the sense that like, okay, let's use the data set and just do the fine-tuning is not going to work out, at least in this scenario. The other problem is that human, when they write the program, it's not always they optimize it for any pattern. No, sometimes some of the changes is slower, some of the changes are not actually productive. And we have to go through all this data set and curate the data set and filter all this problem to make it effective for our machine learning model. And finally, we need a high quality data set when we want to do fine-tuning. And how we do that, we kind of get inspiration from RL techniques. Okay, actually, I can move this because we don't have much data, much time. So we came up with some solution that how can we use machine learning to generate some high quality data points. So what we did is we go to the machine learning model and say, okay, I have this. So these are already fine-tuned model. We have some sample program in our data set. We go to the machine learning model and say, can you generate some problem, some novel problem that you cannot see in our data set? And this problem is completely random problem, and we have not seen them. And then we use those sample problem, those novel program, and we put it in our data set, and we use it to fine-tune the model further. Why we need this problem? Because our initial data set only has some limited set of problems, and it's not enough. It's not diverse enough for the model to learn. So we use this self-play technique to generate and increase the number of data points that we have. I'm going to be a little bit fast, so probably I'm going to... Let me talk about this quickly, and then we can conclude. The other technique that we use, it's kind of inspired by RL techniques in the sense that how can we provide some goals for the machine learning model? So before I show you that, when we give the prompt to the model, we don't provide any goal or any metric to it. How we want to do it is that can we actually tell the model when we want to fine-tune it, say that this fast program is 10% faster. It's not incredibly faster. Or it's like 20% faster, it's 30% faster. So we bucketize the amount of speed up that you can get from different optimization technique. And we use this kind of bucketized data set to fine-tune our LLM model. And during testing, we have this slow program. We ask the model, hey, can you optimize it 10 out of 10? I want to kind of do the maximum optimization that you can do. And it turns out doing such fine-tuning and testing for the LLM, it can be incredibly effective. Okay, this is the interesting result. Using this fine-tuning and self-play techniques, we show that on average, we can kind of surpass what human can do in terms of code optimization. And this is pretty exciting result because we don't need to go through any tool, any profiling or anything. We just rely on the LLM to automate this process. Another disclaimer here, This is not one-shot example. We asked the model to generate 8 examples, and we picked the best one. I want to give you this kind of, but still, this is cheaper than other optimization that human does. This is a lot of data I'm going to skip. You might be also interested about the range of optimization. You might say, okay, this is probably only the model only does like some simple optimization, and it's not that interesting. Actually, we went through the data that is generated by the model, and it seems more than 34% of the optimization that we observe is algorithmic optimization. The code is completely changed. For example, instead of recursive, the model uses like some sort of dynamic programming. So the model shows some reasoning capability that can understand the code and change the algorithm in a way that is more optimal. Some of the other optimization is just the input-output operation, like if the code is I/O bottleneck, I'm using like a C standard methods for reading the data. The model used some data structure modification. For example, instead of traditional array, instead of using STD vector or other, use traditional array or less pointer. And finally, there are like some range of optimization, like removing unnecessary library, unnecessary initialization that can help us to optimize the code. Okay. I'm going to skip this. So some of the potential next step that we are taking for this promising result is that how can we use machine learning or LLM as a compiler pass, basically? So compiler doing a lot of optimization, teach the model to do, can we teach the model to do some of this optimization for us? The other thing that I'm very interested about is about self-refine. We recently published a paper on NURIS last year, which talks about how we can provide feedback to the model to optimize its initial answers. So we think that we can use such methodology to use this feedback in a loop of code optimization. Let's say the model generates a code, we kind of observe it, we provide a feedback to the model, and we can use this iterative process and feedback to further improve the optimization. Okay, I don't think I have time to go through the other part of the talk. I think with that, I can conclude. And if there is time for a question, I would be happy to answer. So the question is about the correctness. Actually, this is a valid concern. So what we did is we relied on the existing unit test for each program. It's an extensive set of unit tests, but still this is a valid concern that you may kind of miss some of the correctness of the code. So currently we just rely on the existing unit test. Yeah. So the question is about how can you differentiate between infeasible and feasible data point in your data set? So infeasible is like mainly is because like the model cannot run an application for some timeout. Like let's say you provide like, hey, for this code, I want to after 2 hours it's finished. So either the timeout, the model because the hardware is not optimized, it takes longer. So we have timeouts. We have compiler is not ready to generate this. So we'll rely on that. And the other one is like some hardware limitation. For example, we go to the hardware people and say, hey, can you build this chip for us? And say, no, it's not possible to build this chip for various reasons. And also there is area constraint. So when we generate a configuration, there is an area constraint and we say, okay, we consider this as an infeasible data point, basically. Yeah. Hey. Okay.
Let's say with an network, at some point it might not actually be doing at all. So do you think, I think in this case, you're comparing against RTL simulators or something.
Do you think this approach and making fast?
So let me rephrase the question. So first is that the simulator is much easier to generalize, basically, right? I disagree, actually. And I mean, you have done like Gen 5 or other codes, it's not very easy to generalize it for a completely different thing. It takes a lot of time. The same problem exists for LLM, I understand. If there is data out of distribution data, the model miserably fails, right? But at least I think for the similar distribution, I think it's much easier for the model to learn out of data compared to asking a software developer to go through the simulator and change all these different changes, right? I think, but if you completely change your hardware, I agree with you. The model, and both the model I think is challenging, and also the simulator is going to fail miserably. I mean, it's not going to fail, but it takes a lot of time to kind of get to your problem. I think the problem exists for both scenarios, honestly. Okay. Oh.
Also work for other domains that apart from machine learning, you had enough data.
So the that's a very general question. So are you asking like machine learning kind of technique can be used for different problems? Like what is the specific? Oh, different kind of accelerators. Sorry. It's hard to say yes or no answer. It really depends on your data, the quality of the data that you have, and the problem that you're defining. So one of the challenging that we have, for example, for this problem that was kind of interesting for machine learning people to work on it is about this invisible data point. Like generally, when they face the problem of optimization, they have a continuous way and like very kind of easy to use like a stochastic gradient descent to optimize it. So it's hard to say yes or no to your problem, to your question, but with enough data and with enough high quality data, possibly we can rely on machine learning to mitigate some of the problem that we are facing. I will be available. Yeah. Thank you so much.
So how to share screen? Okay, thank you. Okay, this was the introduction. Good morning, everyone. My name is Zheng Liu, and welcome to my presentation on on-device LLM. So, deep learning has profoundly transformed our daily life. And as these models growing bigger and bigger and increasing in the sophistication and the power, they also expand their sizes. So however, in numerics practical applications, we are required to deploy these models on mobile devices. So given the computation power and the storage capacity limitation to these devices, it becomes crucial to employ model compression techniques. So in today's talk, I will be discussing our recent progress in making LLMs more compact and deployable on devices. Specifically, I will discuss 3 of our recent works, including mobile LLM, LLM-QT, and LLM-FP4, which focus on reducing the size and the computational demands of these models for practical implementation and also real-world hardware. So in past few months, our team has been working on optimizing LLM to operate efficiently on devices such as smartphones and wearables, while preserving their performance and accuracy. To accomplish this, we developed architecture designs tailored for LLM with sub-billion parameters. The architecture also proposed mobile LLM have been optimized by considering the constraints of the storage limitation in edge devices. This work was conducted with my colleagues in Meta. So when discussing the on-device large language models, 3 questions primarily typically arise. So first, why there is a need to deploy on device? Second, how can we execute LLM on device? And what are the associated constraints? And third, what are the capacity and how well the small models can perform? So in today's presentation, I hope I can answer these questions and give you a comprehensive overview of the on-device LLMs. So contemporary LLM products such as ChatGPT are predominantly designed to operate in the cloud environments. However, there's increasing demand for deploy LLM on portable device, which necessitates small model designs. For example, the memory hierarchy of the mobile devices is typically depicted in the figure. The DRAM capacity ranges from like 6 GB to 12 GB. Given that DRAM is shared with the operation system and other applications, a mobile app should ideally consume less than 10% of the DRAM size. And this motivates us to develop the sub-billion sized mobile LLMs that can effectively utilize the limited resources available on these devices, and while still delivering high quality results. By doing so, we can enable more efficient on-device language assistance, which has the potential to revolutionize the way we interact with our devices. So previous smaller LLMs are not optimized with model size. It leads to the suboptimal performance. So for example, models like OPT and GPT-NEO, they were designed for the hundreds of billions bonus parameters with their and their sub-billion variants are merely serving as an intermediate byproduct using the scaling law to scale down from the larger model size, variants. So also the PySeer is a dishonest suit, which is not designed for architecture specifically for small models as well. So to fully harness the potential of sub-billion-sized models and enhance their performance, we have meticulously tuned the architecture for mobile LLMs to utilize the weights more effectively. The results demonstrates that it can achieve significant accuracy improvements compared to the previous SOTA models of smaller sizes. So what exactly did we do for mobile LLMs? In the design process of mobile LLMs, we initially experimented with various techniques proposed in the super billion parameter models, and we identified 3 techniques that are truly beneficial to the super billion size models, including sweet glue, embedding sharing, and group query attention. By integrating these techniques, we establish a strong baseline. Furthermore, we propose the use of deeper architectures and develop a blockwise layer sharing method to further enhance accuracy without increasing the model size. Now let's dive into the specific details of each design choices and understand how they contribute to the overall performance of mobile LLM. First, we follow the Llama paper to use sweet glue in the feed-forward network, replacing the vanilla FC ReLU FC structure in the OPT models. With this change, the performance of a 125 million model is boosted by 1.3 points on the zero-shot reasoning tasks. Then there is a prevalent belief stemming from the scaling law paper that suggests the performance of large language models is primarily determined by the number of parameters, the size of training datasets, and the number of training iterations. This belief concludes that the architecture design have a negligible impact on the LLM performance. So, however, our findings indicate that this may not hold true for the smaller models. Our experiments with small models of limited capacity shows that increasing depth is more beneficial than increasing the number of channels for the performance enhancement. We trained models with around 125 million and 350 million parameters, varying in their depths with the similar parameter constraints. These results consistently show that deeper and thinner models outperform the shallower and wider ones on various tasks. As we can see from this figure, so those red lines corresponding to the deeper models achieves higher performance on zero-shot reasoning tasks and the question answering tasks compared to those green lines with shallower variants. In addition, in the sub-billion scale language models, the embedding layer make up a large proportion of the total parameter count. For example, in a 125 million parameter model, they account for over 20% of total parameters. However, in large language models like Llama 70B, the embedding only accounts for 1%. So this leads us to revisit the concept of input-output embedding sharing. So as we can see from the table, by implementing this embedding sharing in a 125 million model, we reduce the parameter count by around 12% with only a minor 0.2 point drop on average accuracy. These saved parameters can be reallocated to add more layers, resulting in a more compact and efficient model architecture. We also incorporate group query attention into our small model design, and by reducing KV heads to a quarter of the query heads, we can achieve a 10% model size reduction with less than 0.2 points drop in accuracy. And also, our findings indicate that deeper layer improves the small language model performance, and we further explore the layer sharing to increase the hidden layers without extra storage costs. Surprisingly, it's just by just replicating the transformer blocks, we can enhance accuracy without architecture changes or size increases. We also examined three different layer sharing strategies, including immediate blockwise sharing, repeat all over sharing, and reverse sharing. So this table shows that the repeat over layer sharing strategy performs best. However, given the hardware memory constraints, whereas the SRAM for computing is typically limited to around 20 megabytes, which can only hold a single transformer block. To avoid transferring weights between SRAM and the DRAM, we choose this immediate blockwise sharing strategy, which computes the weights in the SRAM directly without moving it from DRAM and SRAM. And by incorporating all our design choices, we developed mobile LLM, which shows the good performance over the zero-shot reasoning tasks and also other tasks. So in this benchmark, this can achieve the mobile LLM 125 million model can achieve the performance boost of like 4 points, and the mobile LLM 35 billion can achieve like 5 points boost. Also, this latency result shows that mobile LLM can operate at 50 tokens per second and is about 10 times faster than the previous 7B model solutions. Through the weight sharing and doubling the layers, mobile LLM layer sharing version only sees like 2.2 increase in the loading and the initialization time, and only see a 2.6 overhead in the execution time. So it's benefiting from the data locality. So in contrast, if we just directly have a city layer non-shared model with 2 times weights and without sharing the weights, it will see nearly 2x increase in the loading and execution time. So we also like for the we also fine-tune it on the chart data sets and evaluate on the alpaca eval and the MP benchmarks for like to measure the chart qualities. As this table shows, the mobile LLM can significantly outperform the previous SOTA superbinary-sized models. And also, it's notable that mobile LLM 350 layer sharing models achieve like a 48% win rate compared to the baseline GPT-3 model. And given that GPT-3's self win rate is 50%. So it is impressive that a small model like 35 million can achieve comparable performance as the baseline model GPT-3. And here we also showcase some example of chart performance generated by mobile LLM 125 million model. And we can see that it can generate coherent and relevant responses. And also for the, this is another example. Okay, in addition to designing compact models, it also crucial to compress the existing models through quantization, and so quantization is a key techniques. So I will briefly introduce our work on the mobile LLM QEQ, our work on LLM QET. So the majority of the quantization efforts for large language models have predominantly focused on the PTQ methods before the LMQT. So the PTQ is inherently susceptible to the quantization errors. And prior to the development of LMQT, the focus of the quantization were primarily on the weight only or the 8-bit quantization. So in this study, we proposed quantization-aware training to mitigate the accuracy degradation by fine-tuning the quantized models. So QET compared to PTQ, it offers superior accuracy and a higher compression ratio. However, it presents additional challenges. The primary challenge is that it needs a representative data set for fine-tuning the large language models, because the large language model is known as its good generalization capability, right? So if we fine-tune on some model, it needs to preserve fine-tune on some data, it needs to preserve the generalization ability on the zero-shot tasks. So so since for the large models, the pre-trained data set is typically extensive and sometimes even inaccessible. So that it prohibits people from fine-tuning the larger models on some pre-trained data set. So to mitigate these two challenges, we propose our solutions. We first propose generating the data from a pre-trained language model. And then we demonstrate that we only need to generate 100K sentences for fine-tuning the quantized model, and it can yield satisfactory accuracy. This process only requires like 1 to 2 days on 8 A100 GPUs for fine-tuning a Llama 7B model. The comprehensive training procedure for the LMQET contains two stages. First, we generate data from the pre-trained model using the next token generation, and the next token is sampled from the top K candidates. Second, we utilize the generated data as an input and the full precision teacher model prediction as the labels to guide the fine-tuning of the quantized model. So maintaining the zero-shot generalization of the LLM after quantization is crucial, as we mentioned before. So the choice of fine-tuning dataset is important because if we choose a narrow or divergent QAT data, it can harm the performance for the generalization. So for example, if we choose a small sub-dataset from the pre-trained dataset, like if we choose Wiki 2 or Wiki 103 here, it will lead to some overfitting. And even larger model, even large data sets like C4 cannot preserve the overall per-training data distribution. So it will cause some drop in the final zero-shot accuracy. So instead, we suggest to use our generated data. It can closely mimic the per-training data set distribution. This approach, as we can see here, it shows better performance compared to the subsets of the per-trained data. Of course, if we can obtain some real per-trained data, this the gap between the generated data and the real pre-trained data will be smaller. But if we only have some subsets of the pre-trained data, it cannot cover the whole distribution of pre-training and will lead to some accuracy loss. And in this case, we have the solution of generated data, and the generated data shows some like superior generalization ability on the zero-shot reasoning tasks. We suggest to use sampling process instead of the only the pick the top one choice in data generation process. Okay, so for the quantization function, we simply choose the min-max quantization because empirical findings suggest that preserving outliers is crucial when quantized LLMs. This table compares the results, and we can see that LLM methods, LLM QAT, and can well perform on the different data sets. And also, a critical question is, in what kind of bit width should we choose for the quantizing the models, and when we want to deploy a model on device or want to have a more compact model? So the answer is like for the 8-bit quantization, even PTQ can work very well. It can generally outperform small model with full precision bits and with half number of parameters. Like for example, a 8-bit 30-bit model, quantized model, can surpass a similar final size 13-bit model with full precision weights, and it can offering lower latency and higher throughput with an 8-bit model. However, when either weights activation or KV cache is quantized to less than 8 bits, the post-training method just leads to accuracy degradation. In this regard, LLM-QAT can significantly recover the accuracy loss. Furthermore, the 4-bit model quantized with the LLM-QAT should be preferred over the 8-bit models of similar final size. For example, W4A8 LMQAT Llama 30-bit model can outperform a 8-bit Llama 13-bit model, and also a W4A8 LMQAT 13-bit model is better than 8-bit 7-bit model. So as a result, we recommend to use 4-bit LMQAT models for the best efficiency and accuracy trade-off. And so the takeaways are here. So for the quantization fine-tuning, generated data can better preserve the zero-shot generalization ability in the quantized models if we don't have the full pre-trained data at hand. And we can use the min-max quantization to preserve outliers. And also, given the final model size, some performance hierarchy is 4-bit models is better than 8-bit model and better than 16-bit model. Then to further enhance the performance on low-bit quantized models, we have also investigated floating point quantization method, and we developed LMFP4. This is a post-training quantization method, and it uses floating point quantization. The motivation is that the existing post-training PTQ solutions for LLMs is predominantly rely on integer-based methods and face challenges with bit width below 8 bits. Meanwhile, FP8 and other floating point formats has evolved as a standard choice across various hardware platforms, including the NVIDIA H100. So further generation hardwares will naturally support the floating point quantization method. So as we know, like a significant challenge in quantizing large language models is managing the outliers. Those visualization clearly shows the outliers are not exclusive to LLMs, but also present in the BERT and vision transformer models. Outlier can dominate the quantization precision of the quantization tensor, reducing the representation capability for the other elements in with the small magnitudes. So, but the good news is, those outliers exhibit a noticeable pattern. They are predominantly confined to several channels. So there is a solution. Also, we cannot directly apply per channel quantization for activations because it is not aligned with the matrix multiplication direction. And if we directly apply channel-wise activation quantization, it will lead to some inefficient matrix multiplication. So, what our solution will be? We propose this per-shift exponent bias, leveraging the characteristics of the 14-point format to migrate those high channel-wise variance problem. This per-shift exponent bias is achieved by we initially decomposing the channel-wise bias, channel-wise scaling factor into a tensor-wise scaling factor and plus channel-wise scaling factor. So channel-wise scaling factor is 2 to the power of BORI. This BORI is an integer, and it can be reparameterized into a weight tensor as the exponent bias for the weights in their 14-point representation. So during the inference time, we just pre-compute the weights and the exponent bias in the calibration phase. Consequently, those exponent bias shifting process only occurs during the calibration stage, allowing the efficient multiplication during the inference time. Okay, so this final slide, the experiments for the Llama 7B and 13B models shows that our proposed floating point quantization can achieve near lossless results on W8A8 and W6A6 bit choices. So it is a challenge test originally for the PTQ with integer count, and specifically with ultra low W4A4 precision, the SOTA PTQ method sees significant drop. So LMFP4 can effectively handle those ultra low bit settings and sees only 5.8% average drop on the social recent tasks. This is like a very good result for the W4A4 experiments. Yeah. So thanks for the listening and any questions?
So honestly, everybody wants to go on device level. I mean, why should we not go on device level?
Good question. It depends on like the use case, right? Sometimes if we want to batchify different users' input and maximize the throughput, we might want to use the cloud that we can collect different users so that we can like process it through our batch. And also like of course servers are more powerful and they can like hold larger models, and some use cases they are difficult, so we want a larger model to handle that, so we might use server model instead.
If I want to have a search on my phone, it's like saying, well, I can't give you the whole internet, so I'll give you a shard of the internet. You see the analogy of things? That's where I often struggle, which is like, I know that I always want a really good LLM. So why would I want to compromise that quality? That's the fundamental question that I often struggle with, even though from a responsiveness, all that it makes perfect sense.
Yes, I totally understand. But sometimes we don't want to share our personal information with the cloud service. For example, if we want to use it in hospital, we want to like analyze our health data. So we don't want to share that kind of privacy information with cloud server. Or you don't want large language model train all your data, and sometimes you will leak your data somehow someday. So we want maybe it's more safe. We can hold the language model on our device, and it's not shared with anyone else, not shared with the cloud server, and our data is on the phone, and we can have full control of data in the model. So that's a major reason for why we want to have this on device LLM. Thank you.
This Asian property. Aisha is a senior researcher at Microsoft in the Azure Research Systems Group. Our current research focuses on efficient AI in the cloud and the layers of AI platforms, hardware, and research design integration. In the past, Aisha has also worked on sustainability, learning systems, and profession. He has a PhD from UC Austin and has published 7 papers at top 300.
Sorry.
It might be because I see. Can you just share the screen instead?
Yeah, let me try. I think like
It might be because I have this
you have
video kind of thing on the first slide, and it might just be big size. Awesome. Thank you so much for the introduction, and thanks for setting this up. So hello, everyone. I am Isha Chokse from the Azure Research Systems Group at Microsoft. This doomsday picture of the rapid growth of GPU in DCs is actually something that we tackle day to day with. So I'll talk a little bit about how bad it really is, the power and energy wall that we are currently running into, and introduce a couple of works that we've done in this direction in order to make LLM deployments more efficient. All right, so let's get started. So how rapid is this growth that I'm talking about? The screenshot is from a couple of months ago, but this is when Meta and Mark Zuckerberg announced that 350,000 NVIDIA H100 GPUs will be added to their fleet in by just the end of this year, right? The reason I'm using this is because this is the only company that publicly talked about the number of GPUs that they're going to be adding. Now, that is a lot of GPUs. And if you think about the power that adds to the Meta data centers, that will be 437 megawatts of additional power in 1 year at Meta, just talking about these particular H100s. That is enough power for a town of 150,000 human beings. Now, this was just Meta. If we expand this number and kind of also provide for the scale at which Microsoft Azure, AWS, and GCP use GPUs, we're actually talking about around 8 gigawatts per year being added to the data centers just because of the GPU expansion that we're looking at. That is more than 0.6% of the total US grid when it comes to power. The current projected annual growth in US electricity is just 1% per year until 2050. So we're talking about taking up 60% of the additional power that's coming year over year in the US grid just for data centers that are meant for LLMs. This is a graph that was provided to us by the PJM grid operator from the Virginia Data Center Rally. So this is, you all probably know that 35% of the data centers across the world exist in Virginia. In fact, you can drive by this data center rally, and all you see is giant gray boxes on the sides of the road. So Dominion is one of the power operators or utilities in this region. And if we look at their power estimates, look at how it has increased from 2014 to 2023 for data centers, going slowly from 0 to 5 gigawatts. But in the next 2 to 3 years, we'll be seeing a doubling of that gigawatt number just in Virginia. And the growth that they're expecting in terms of demand is just exponential. This is, of course, being met with a lot of pushback from Virginia residents, from the government, all of that, right? So we're quite literally running into a power wall. Prime power is something that, so the max power that the data center can operate at is the prime power. That's the power that's needed from these utility companies. And we're literally running out of them. The utility companies are coming back to us saying that you cannot build more data centers in this region. We just don't have enough power. In the next 5 to 10 years, we will probably see a lot of requirements for flexibility and load shaping from the grid, right? Because you'll be seeing that even though they're able to add power to the grid, it's only from certain sources that are not as reliable. It is coming at the cost of running these data centers at peak when the rest of the world is not running at peak, right? So load shaping and just demands for flexibility. These are things that we are already getting from the grid, honestly. But these will start becoming more commonplace in the next few years. We'll also most probably see data centers with their own energy sources, sort of taking reins into their own hands since the utility companies are saying no. So this is where we are headed towards. But what until then, right? So if we look at the data center picture, like the end-to-end data center picture, we have this power supply part that includes the transmission and distribution, the power supply, the backup generators, all of that, right? Then there's the critical IT load, the part that we are all most aware of. So there's the chips, there's storage, everything as a part of server, the network that goes into each room of the data center, or colo as it's called. There's the cooling and heat removal equipment that is generally something that's separate from the data center, but at the same site. And then that's the part that the critical IT load corresponds to. So in terms of, so I guess the point I'm trying to make here is that the power supply part is not really scaling at the rate at which we want it from the critical IT load perspective. And so for the next 5 to 10 years, all we can do really is to ensure that we sort of throttle our demands of the critical IT load to match the kind of power supply that we are able to get, right? So talking about power efficiency and in the critical IT load, this is something that has been around in the CPU world for decades. I'm sure you all have read several works from cloud service providers, including our group, in the past that have worked on using various power features for efficiency that CPU vendors like Intel and AMD have been building on for years. However, let's see how that compares to what we have in GPUs today. So we're all quite familiar with these kinds of graphs. It's a power versus frequency graph. And then we have several lines for one core active versus n core active, right? We want to make sure that if we want to run in a power efficient or energy efficient way, we would want to generally, for the right workloads, bring down the frequency to the right point that allows us to have as much performance at a lower power. So let's compare the features that we have. Process priority, right? So this is something that has existed in CPUs for a very, very long time. You can have a lot of processes running together, and you can choose which process has higher priority over the other. Something very basic that we take for granted in CPUs, not available in GPUs today. Per core voltage domain. This is something that is very key to lower the idle power in any data center scenario. Again, something that is heavily used in the CPU world. In GPUs, it does not exist, right? We have a single voltage domain for the whole GPU that even includes the memory side of the GPU or the HBM. Then there's per core frequency control, which allows better power perf, something that I was showing on this graph. So you might have come across a lot of DVFS related papers that make use of all of these features in the CPU. But in GPUs, you can only set the frequency for the whole GPU at once. And then there's performance versus energy efficient modes. Again, something that you're probably most familiar when using a desktop or laptop, running your system in an energy efficient mode when you're running out of battery. It's also something that is used heavily in data centers in order to ensure that during peak workload times, some of the nodes are run in an energy efficient way so that the other nodes can run at max perf. Again, not a mode that's available in GPUs today. When we step back and then look at what kind of power numbers we're talking about, there are all of these features in the CPU world where the average or even max for a lot of scenarios, the max power per node that we're talking about is like 700 watts per node. For GPUs, a single node is 10,000 watts per node. This is a DGX H100 that I'm talking about, which will have 8 GPUs with 1,200 watts per GPU rating. So it's obvious, given the power and energy wall and given the scenario that we are in with respect to increase in building out GPU data centers, that we need to really act fast. CPUs, of course, took 2 decades of slowly evolving all of these features, but unfortunately, we don't really have that kind of luxury of time, and we need the solutions today. So we need to make sure that with the existing feature set that we have, we need to deliver efficiency such that we can meet the gaps. So let's ask the question, do we really need all that hardware? So we were talking about 350,000 NVIDIA H100 GPUs, right? Do we really need all that hardware for the workloads? And does that hardware really need all that power? So I'll try to answer both of these questions by introducing a couple of works that we've done in this direction. So do we need all that power? For training, unfortunately, yes. Training tends to be a very synchronous, large job, something that's run across tens of thousands, sometimes hundreds of thousands of GPUs. And of course, being at Microsoft, I'm talking about the larger models that are trained. So these large synchronous models, when they are trained, all of these GPUs would go into their compute phase versus communication phase together. So as you can imagine, during a single iteration, you have a lot of compute happening together, and then between the forward and backward pass and at the end of each iteration and every time that you're checkpointing, you would have a lot of communication happening. Now, GPUs make up more than 60% of the power of each node that they're part of. And the GPU power is quite high. It's actually at its max level when it's going through this computation heavy phase in the training iteration. But when it comes to the communication heavy phase, it kind of goes down to almost idle power. So when a training job is happening, think about tens or hundreds of thousands of GPUs doing this together and kind of going up and down in their power utilization. But when they go up, they actually go up to the 100% mark. So all the allocated power to these giant data centers is actually being used in each training iteration. So unfortunately, the answer to do we need all that power right now, with the current hardware, with the current models, the answer is yes. However, when we look at LLM inference, we saw an opportunity there. So we collected a lot of data from data centers that were serving various types of copilots, various types of GPT-4, and we saw that the max power utilization in a data center row, which is generally comprised of tens of racks, was less than 80%. The reason for that is because of the inherent nature of the workload. So during an LLM inference, you would have two main phases that I'll shortly talk in detail about, but there is a prompt phase or a prefill phase and a decode phase or the generation phase. These two phases are inherently different from each other and have different kinds of power utilization pattern. So in a data center, when we look at a high enough aggregation level, we actually see a statistical multiplexing of these two phases happening during LLM inference, which means that some percentage of the nodes are running at low power utilization. Some of them are running at high power utilization, even though they're all active and doing very important work. So this is where we saw our window of opportunity to do some power efficiency work. And we thought we should be able to oversubscribe this power, which means instead of giving all the 100% allocated power to these LLM inference clusters, what if we only give them 80% and then have a back end that is able to kind of track if the power goes above what we predicted and come in and throttle these servers if needed. So that's exactly what we tried to do. However, we came across several challenges in that. One of them is that even though there are frequency and power throttling mechanisms that are available in GPUs, GPUs today across all the clouds are direct device access mode into VMs. What that means is that the cloud service provider actually does not have access to any in-band drivers of GPUs. So the only thing that the cloud service provider has access to is the out-of-band mechanisms, which unfortunately aren't great. So remember the earlier power perf feature set that I was talking about? It was already pretty small. When it comes to out-of-band, it's even smaller and much slower. So we're talking about a 40-second delay in setting a power limit or a power cap. And this was in A100s. For H100s, we worked with NVIDIA, and now it's much better. But for this work, which actually is going to be presented at ASPLOS on Tuesday, this was work done with our intern, Pratish Patel from UW. So this is work where we kind of go deeper into this training power versus inference power, and what are the various patterns, and how can we oversubscribe power despite the gap in the current telemetry and control in GPUs. So what we've done really is chosen thresholds based on the known maximum power spikes across the past 40 seconds. And if things go much worse, we actually use a heavy hammer called power break, which would bring down the GPU frequency to 200 megahertz here, essentially doing nothing at that point. But a combination of these two things was able to give us at a P99 impact of just 5% latency performance, we were able to oversubscribe power by 30%. So essentially adding 30% more servers in the same existing data centers under the same power budget without asking the utility for more power, we were able to add these racks. So that is something, for more detail on this work, please attend the talk that the intern will be giving. And of course, keep in mind that with newer GPUs, with newer hardware, with better telemetry and control, this work can be even better. Now, let's go back to, do we need all that hardware? So we were talking so far about how much power can we, without changing the workload, right? How much power can we reduce? But also, it's better to use 70 servers at 70% utilization than 100 servers at 50% utilization because of the obvious problem of the idle power, right? The idle power problem has existed in the CPU world, again, for decades. In GPU world, it's much worse. An idle power number for DGX H100 would be somewhere between 4,000 to 5,000 watts out of a 10,000 watt TDP. So that's around 40 to 50% of the power being idle power. So we looked at the LLMs, and of course, like all the previous talks have talked about, LLMs can run both memory capacity and memory bandwidth bound. And if you look at the power, memory is just 20 to 25% of the GPU power. However, that is the critical part of it, which forces the rest of the GPU compute to actually run underutilized. And so with all of those insights, we tried to break open the box. So instead of doing this closed box approach that we did earlier in the previous work, we kind of went into the LLM and saw what is it that we can change about it, right? So I talked briefly earlier about the two phases. Here it is in detail, right? So there's a prompt phase and a token generation phase. When you ask a question, all the tokens in the question get generally, depending on the batching, get batched together and go through the forward pass of the LLM together, right? So that is the prompt phase. And then the serial part of the transformer token generation happens one by one, where the only new data that has come from the last iteration is the last generated token. The rest of it is coming from KV cache, right? So the obvious differences between the two phases, the memory capacity needs of the prompt phase is way lower per active batch token compared to the token generation phase. The memory bandwidth need, again, is way lower for the prompt phase compared to the token generation phase, because in the token generation phase, for each active token, you're accessing the whole KV cache of that request so far. In terms of compute needs, since the level of parallelization is different, prompt phase is way more compute intensive compared to the token generation phase. And since the power intensity lies in computation, the pattern duplicates. In terms of time spent, of course, that depends on the workload in terms of how many input tokens and how many output tokens you have. But generally, you would spend less time in processing the prompt compared to the generation phase, because for generation, for each token, you're actually doing a full forward pass. So the break-even point would generally be around 5 tokens. So if you're generating more than 5 tokens, you're spending more time in the token generation phase. So since we are kind of running out of time, I won't go into details, but all of these plots in detail are in our splitwise paper, which is about to be published at ISCA, but also the link is on our website. So the other motivation that we had was with respect to the hardware that was coming out. So if we compare H100 to A100, the teraflops have increased by 3x. Which means that the compute capacity has increased a lot. But if we talk about the memory capacity, it did not increase. The memory bandwidth increased because we went from HBM2 to HBM3, but that also increased only by 64% compared to how much the computational intensity was able to increase. The power increased by 75%, and the cost became more than double. So given that we talked about the prompt phase versus the generation phase, the obvious intuition that we had was H100 should do better than A100 on the prompt phase, whereas A100 should be better, more cost effective, more energy effective than H100 for the token generation phase. And that's exactly what we saw in our experiments. So all of these experiments are with Bloom 176 billion, but we have also presented the results with Llama 270 billion in the paper. So this took us to the idea to split the inference phases onto separate hardware. So this is where Splitwise comes in. Again, with the same intern, Pratish Patel from UW. It will be at ISCA, published at ISCA 2024. So the main idea is to split the inference into these two phases and run them on separate hardware. what this allows us to do is these two phases are now running on separate machine pools that can be sized accordingly. The model can be sharded, the parallelism can be changed on these two phases accordingly. They can even be running on different hardware. So we're talking about heterogeneous compute here. And they can run at a different power perf point. So we could actually underclock for the memory bound phase, which is the token generation phase, while run at the maximum frequency for the compute intensive phase. So with our experiments, this actually unlocks up to 80% more throughput at the same power with no change to the model at all. It's purely a cluster design, model deployment, and scheduling kind of change. So at a high level, what we're talking about here, of course, since the prompt phase and token generation phase are separated, there has to be context that goes from one server to the other. So I've overly simplified it here. Of course, this is also applicable to models that go beyond one node, but let's assume that our model is only split across 8 GPUs on a single server. So there's a prompt machine, there's a token generation machine, and we are doing the forward pass layer by layer. So as the layer 1 gets computed, the KV cache associated with it gets computed. And while the layer 2 forward pass is happening, we would transfer the KV cache from layer 1 onto the token generation machine. What this allows us to do is to overlay the prompt computation time with the KV cache transfer time so that our overall impact on the end-to-end inference is quite low. It's actually less than 0.8% impact, even for the largest prompts that are supported by the model. So in terms of evaluated designs, since splitwise allows us to kind of design these clusters for the prompt phase and token generation phase separately, we played around with the design quite a bit. So we used A100s for both prompt machine and token machine. So this is splitwise AA. Splitwise HH is H100 for the prompt machine and the token machine. Then there's HH cap and HA, where we went heterogeneous. So H100 without any power caps was used for the prompt phase, but H100 capped at 25% at the GPU level, which comes out to I think 75% of the power of the node was what HH cap was, and then splitwise HA has prompt on H100 and token on A100. So yeah, we had a whole system design around this. The main thing to keep in mind is there is a cluster level scheduler that will have to track how many nodes go to the prompt pool versus the token pool, and if there needs to be a mixed pool according to the changes in the workload during the runtime. And what's happening in the back end is the KV cache transfer over InfiniBand, which we implemented using EMC2'24++, which is a highly optimized version of Nickel on InfiniBand. So quickly flashing some results here. Again, detailed results are in the paper. In the paper, we call it code versus chat, but who are we kidding? This is from Microsoft. Code corresponds to GitHub, chat corresponds to Bing. And the kind of improvements that we saw with splitwise HH over baseline A100 was 2.25x. Even over baseline H100, we're looking at an 80% improvement for GitHub. And why it's different for Bing versus GitHub, more details in the paper. So other directions that we are looking at right now, across the layers, we're looking at model, platform, driver, hardware, data center management. We're always trying to look through the lens of power energy. In fact, Jovan Stojkovic earlier, who we are collaborating with, presented the first part, early results from the first part here, which is how do we use the right model and sharding for being more energy efficient. Yeah, so you can find a lot of details about this on our website under the project Efficient AI, which I'm leading. And this is just a pitch. We are hiring, and if you want to do extremely fast research that gets into product within the year, come join us. All right, thank you. I'll take any questions. Yeah, so actually it's the opposite. Like the token generation phase is the one that is more memory capacity bound because for each active token, there is a lot of memory. Now, I think what you're saying is the transfer latency high? Uh-huh. Oh, it's the opposite. Yeah, so like it's lower for prompt versus higher for token. During token generation, it is. Like it is more memory bound. So yes. Correct. Yes. So you would want to essentially, if you're deciding how the model gets sharded across GPUs, you would want to do it very differently for token generation phase such that it gets less compute, but a lot more HBM, right? Sure.
Our next talk is by our sponsors, EMC2'24. And we are grateful for their continuous support for several years. The speaker is Sri Ganesan. She is the Vice President of Product at the Matrix, started building innovative compute platforms for generative AI. Prior to that, she was at Intel, leading software strategy for first Nirvana and Nepal. She has a PhD from University of Cincinnati, Ohio, and a bachelor's degree from Ivy.
Hi, everyone. Thanks to those of you who are still sitting here. I know I'm the last barrier between you and lunch, but I'll try to make it fast. I wanted to talk about transforming generative AI from unsustainable to attainable, which is one of our goals here at the Matrix. So, I don't have to introduce this slide here because this audience has spent a lot of time today talking about, what is, what's going on in generative AI and how many explosive use cases they are creating. There isn't one killer app that has emerged. It's just across the board. So many use cases are popping up and there's a lot of exploration that's going on. You can see that there's a lot of talk around exciting new models. There's a talk around how much, how much compute is being used for it. But at the end of the day, it's the inferences that are going to be overtaking them as soon as they get deployed, right? Once the training is done, it instantly switches over to the inference piece of it. And you can see already some examples of the amount of inference that Meta and Microsoft have publicly reported. In parallel to all this excitement that's going on, we hear there is a problem. The demand way outstripped the supply. If any of you here have tried to reserve an H100 instance on any of the cloud providers, good luck, because it takes forever to get those instances. And it's out of reach for a lot of folks because there is such a high demand. And either they're compromising on the performance. Either there's it's slower, or there's a lot of trade-offs that are happening to service this demand. But let's ask the question, why? Why is there this problem that's showing up, and what is the reason for the lack of sufficient compute? So first, obviously, is cost. We hear again a lot about how many GPUs. It's hundreds of thousands, tens of thousands, hundreds of thousands. I think Isha covered very nicely the challenges in terms of the volume of compute and not being able to trade that off. So there's obviously a tremendous amount of cost involved in generative AI training. And power, right? This is the topic of today's talk. It's about energy efficiency. There's a lot of consumption of power in order to deliver that kind of promise of generative AI. And this is when we put into the context of where are all the challenges, it's across the entire spectrum. Again, I want to thank Isha before me because she did a very nice job of laying out the challenges in the power space, so I don't have to double click on it. So we are really competing with, AI could potentially consume more energy than the human workforce. And the other piece is around the size of models, is bigger, better, and we're starting to see that smaller models can actually compete very well in terms of the quality with some of the larger models. So there's going to be this spectrum where, in terms of deployment and in terms of being able to put it in a more efficient way for both cost and power and quality. Do we gravitate to smaller models or I think this is going to be, yes, yet to play out. I think there's going to be a mix in both these very large models and small models and finding the right use cases for them. But at the end of the day, this is all going to just add up to cost. If you make it more efficient, there's going to be more use of it, and that's again multiplies into cost and power. So the generative inference, transformer inference is a kind of a unique problem. Models are very large. This is not the small models we talked about in the past. These are growing very rapidly, especially in terms of enterprise applications. And they're not going to fit on a single device easily. We tend to parallelize across multiple devices. That requires more memory capacity, requires more compute capacity. And the unique nature of transformer inference, you have two steps in the process. One part is compute bound, that's the prompt processing part, and the other part that is token generation is memory bound, memory bandwidth bound. So you, at the same time, for the same workload, require both a high memory bandwidth and high peak compute capacity. So it's a pretty hard problem for a compute platform to solve. And there's inefficiencies in different platforms. And all of this is contributing more to the cost and power and performance pain points beyond what we've seen in the general deep learning deployments of the past. So across the spectrum, right, this is not just around one piece of the story. There is, in terms of power and efficiency, you've got data center level, you have the likes of Azure and others who are doing a lot of work in terms of innovating on that. There's a lot of work that's going on in, climate-friendly technology in terms of alternative power sources to be able to supply that kind of power. In terms of cooling technologies, and there's work going on in terms of compute platforms. You see a lot of innovation across the industry on building more efficient compute platforms. We heard a lot today around algorithmic and software techniques as well. So it's a broad spectrum of contributors that are enabling in terms of reducing the impact of what this kind of transformer-based inference can do. And today I'm going to take a couple of minutes to talk to you about what D-Matrix is doing about it. So first and fundamentally, this is a computing platform, and what we've done is basically really looked closely at the transformer inference problem, identified the pain points, and concluded that we basically fundamentally needed a computing paradigm that's different from today's traditional architecture. So if you're looking at other architectures today, you have compute and memory, and there's data moving between compute and memory. There's a bandwidth issue across, going back and forth. That data transfer is also burning energy. And we have actually innovated and built a digital in-memory computing platform that allows us to put the memory very sitting right in next to compute. And therefore, it allows us to basically really take advantage of that high memory bandwidth and also reduce the energy consumption in this process. So this is a big shift in the way computing is done. And we're among the industry's first in terms of actually productizing digital in-memory compute. We have 3 generations of proven silicon. We proved our first in-memory computing platform with our first test chip called Nighthawk. And then we built our solution based on chiplets. So we have an IP that allows us to talk very efficiently at a high bandwidth across different chiplets. So we demonstrated that with Jayhawk 1 and combined, the digital in-memory computing platform with the chiplet-based solution and demonstrating the die-to-die interconnect with Jayhawk 2. And with this, we basically are at the point where we've proven our foundational technologies, and we are now working on our commercial product. We are going to be launching Corsair, our first generation commercial product, later part of this year. It'll come in a PCIe form factor, and we're going to have a software stack that is optimized to take LLM models and conveniently deploy it and take advantage of it, of Corsair's hardware innovation. Aviator is the name of our software stack. We will integrate it with PyTorch and Onyx. Our software stack is meant to be compatible with any other deployment platform that others are using. Whatever kind of inference serving infrastructure you have, we will make it API friendly in terms of integration. We have custom numerics. We used block floating point, and that allows us to compress and have more efficient data representation. And basically, our software stack will seamlessly convert the numerics to from industry standard formats to our internal block floating point. We will distribute this, compile and optimize this model to run on Corsair. We'll also be able to distribute the workload across many cards and servers, and we have an inference runtime, which allows you to take advantage of some of the innovative solutions that are coming up in the algorithmic space, whether it's continuous batching, speculative decoding, and all of these ideas will be implemented and available in our inference engine. On top of it, you can set up a Kubernetes cluster, and you can manage and monitor your cluster with our software stack. So this is typical, like what you would expect any kind of inference infrastructure. Our focus is on the cloud, basically data center inference. This is where we believe that inference will take off at scale in terms of enterprise deployments. So for both cloud service providers and on-premises, and we will be working closely with partners in this ecosystem. We're working with the server, people who are building servers, the OEMs and ODMs, to put our PCIe cards into servers, build out racks. So, people who want to purchase and deploy on-premise can buy from the server ODMs, or, we'll be working with CSPs as well. So bottom line is we're preparing for enabling and putting it in the hands of developers like you, so you can start doing your innovation on top of Corsair. So the advantage, to summarize, we've got circuits and numerics advantages. This is the technology. It's the in-memory computing, block floating point and sparsity for memory compression. We've got the chiplet-based architecture, die-to-die interconnect, and advanced packaging that goes along with it, and an easy-to-use, performant, and scalable software stack. But the benefit, that's all technological innovation, but the benefit back to the community and the users is that you get better throughput, better latency, better TCO, along with better power efficiency. And so my call to action is, we're growing. We are breaking in terms of technological innovation and ideas. We're breaking those barriers. We're trying to keep innovating. I'd like to invite folks to join us in this journey, either come and work with us or partner with us. We are collaborating with a lot of folks in the ecosystem. Reach out to me, and we will hope to continue to foster innovation through this kind of community. And hopefully by the end of the year, we'll have a product that will allow us to put it in your hands and then unleash your creativity as well. With that, I want to thank you for sitting here, and you can catch me around here. No need to take more time out of your lunch, and thank you so much.